Okay, it's 8:30. Good morning, everybody. We're going to get started. Welcome to the Land Ice Working Group and Polar Climate Working Group session. They're going to be back-to-back this morning until between now and the middle of the morning break and until lunch. I'm Untitled Chapter, the co-chair of the Land Ice Working Group, with Miriam Vizcaino, who is here, and Alice Duvivier, the co-chair of the Polar Climate Working Group, and Ed Blanchard will join us, I'm sure, at some point. Just a few opening remarks before we start the session. I would like to remind you about the code of conduct that we operate here during this workshop. Be respectful with one another, be collaborative, consider different opinion, communicate openly, and be mindful of others. More importantly, I would like to remind people that there's no stupid question. You know, if you don't know something, it's legitimate. Just ask. That's what we're here for. So please don't be too shy and you know, put yourself out there if need be. When you want to ask a question, please use the microphone in the center of the room here so that everybody can hear you either in the room or online. Try not to speak in just openly without a speaker. For presenters coming that are presenting on site, please make sure to adjust the microphone here so that everybody can hear you. And for people presenting remotely, we expect you to share your own presentation. The talks will be a total of 10 minutes long each, 8 minutes for presentation and 2 minutes for question. Kate is going to share the remainder of the session once I'm done up here, and she will be the one monitoring your time and cut you off if need be if you're taking too long. Another quick announcement is that we received emails, by we, I mean the organizer of the workshop, that a few posters weren't put up yesterday, and they're going to be put up today. I don't know if it's necessarily specific to our session, but new posters will be up today until tomorrow. So if you've done your round yesterday, please do another one to see what's new. And yeah, without further ado, I'm going to transfer now to Kate to announce the first presentation.
All right, welcome everybody. Our first presentation is an online presentation. Shirasi Samada from the Indian Institute of Tropical Meteorology. Shirasi, are you there?
Hello. Yeah, am I audible?
We can hear you. Oh,
Yeah. Hi.
All right, please
Yeah.
share your slides.
Yeah, just a second. Okay, so
good.
should I start?
Yep.
Okay.
Nice job.
Yeah. Hi. So good morning, everyone. I am Shrivashi Shamanto. I'm a PhD student from Indian Institute of Tropical Meteorology, Pune. And today I'm going to be presenting our recent work on the accelerated Greenland ice sheet melt and how it influences the South Asian precipitation. Now, this is a collaborative work between NCAR and the IITM. So first of all, before I start everything, I want to thank the organizers for giving me this opportunity to present the work. So let's get started with the motivation of the study, right? So observational near surface temperature trend of Greenland has shown a significant warming, specifically around across the coastal stations of Greenland. Now, this is not abstract. It actually translates into the ice mass loss. So the satellite derived estimates actually show a sharp decline in the ice mass trend of approximately 248 gigatons per year, predominantly during the summer months. So the accelerating ice melt trend is basically the center of our study. Next, what is driving this melt, right? So one of the primary mechanisms behind this melting is the presence of atmospheric blocking patterns or high pressure systems centered over Greenland. Now, we all know about Arctic amplification. So the Arctic is warming at a rate 4 times faster than rest of the globe. So when the Arctic actually warms, it causes the meridional temperature gradient to weaken, and that causes the polar jet stream to weaken and become slower and more meandering in nature, resulting in frequent atmospheric blocking high pressure systems centered over Greenland. But what this does, this actually creates warm air subsidence and enhanced melting over Greenland. This can actually be quantified with the index called the Greenland blocking index. So higher the blocking index, there is going to be more subsidence and eventually more melting. Now, not only the long-term warming in the Arctic, actually climate modes have also been favorable for the presence of frequent blocking patterns over Greenland over the past few decades. But we have seen that for the past 2 decades, approximately, the primary climate modes, such as the Arctic Oscillation, the Arctic Dipole, the North Atlantic Oscillation, they have been predominantly in the negative phase. This is a 15-year smooth curve, but we can see from this region, there is actually a negative phase persisting. Now, this creates a favorable environment for more frequently blocking events to appear over Greenland and therefore enhance the melting over there. Now, not just atmosphere, the ocean is actually also responsible. There is an oceanic contribution as well. During these negative modes of the climate, the wind stress curl over the subpolar North Atlantic region actually weakens. That causes the subpolar gyre to weaken, as we can see from this time series curve, with the red dots being the high melt tiers. Now, what happens next? The Irminger current strengthens. What this Irminger current does, it transports the warm and saline Atlantic water to the southern sections of Greenland. And therefore, it will be reflected in the oceanic heat content. The oceanic heat content will show a rising trend as it has been showing. And we have also checked the composite OHC. It also shows a significant warming near the southern sections of Greenland. This will supply ample heat energy for basal melting of the marine terminating glaciers. Now we further wanted to analyze, we wanted to see other aspects as well. We have seen the heat transport through the southern box of Greenland, and we see a clear positive anomaly for the high melt tiers in the heat transport profile. And we have also checked the OSNAP temperature profile, subsurface temperature profile. We took two reported high and low melt years. 2019 is a reported very strong melting year. We checked for the summer period, we checked the subsurface temperature profile. We see clear warming signal here. This passes through the southern sections of Greenland. And for the low melt year, there is a clear cooling pattern visible. This year, this just summarizes the oceanic contribution to the Greenland ice sheet melt. Now, after that, we were curious if it has any impact on the tropical region. So there are studies that have already shown that the Greenland ice sheet melt can impact the mid-latitude weathers. But we wanted to see if at all it has any impact on the tropical region. For that, first we have tracked the seasonal SST progression, and we have seen something really interesting. In the previous winter, there's a strong El Nino sitting in the Eastern Pacific region that has slowly transformed into a La Nina-like scenario, significant La Nina-like scenario in the summer monsoon season during those high melt composite analysis. Now, this is important because this will be reflected in the precipitation anomaly, precipitation responses, as La Nina generally in the Pacific generally means there is going to be enhanced mean summer monsoon precipitation over the Indian subcontinent, as we can see again from the composite analysis for those high melt years. So now we wanted to isolate the impact of the Greenland ice sheet, right? So we have designed this experiment where we use IITM ESM, which is a fully coupled ocean atmosphere global circulation model. And it has been developed in the IITM, and it has also contributed in the CMIP6. So we take the CMIP6 configuration, we first run a historical simulation from 1950 to 2014, and there is no Greenland meltwater forcing. Next, what we do, we take CISM, we configure it for the Greenland. We first perform the spin-up analysis, and this is the ice thickness and the surface mass balance signature at the end of the 45,000 years spin-up procedure. Then what we do, after configuring the CISM, we take precipitation and near surface temperature from the IITM ESM. We force the CISM with said variables, and then from the outputs from CISM, which is the accumulation and ablation, we basically take surface meltwater runoff and the basal melt from the Greenland, and we again feed it back to the IITM ESM. So this simulation, we again perform another simulation from 1950 to 2014. We name it HIST plus GRIS. This is identical to the historical run, except with the additional Greenland ice sheet runoff from the CISM. So basically, any difference between these two simulations are going to be due to the Greenland meltwater. Now, again, we do the same composite high melt cases analysis. For both the simulation, we take the high melt cases, we do this composite analysis, and the response is really clear. We see a clear freshening at the subpolar North Atlantic region in the with melt experiment. And this actually triggers a series of events. So when there is a clear freshening seen over the SPNA region, the subpolar low is going to weaken, the mid-latitude westerlies are going to weaken and shift equatorward. That is going to weaken the Azores High. Now, Azores High is really important because Azores High actually fuels the northeastern tropical Atlantic trade winds. So when the Azores High will weaken, the northeasterly tropical Atlantic trade wind is going to weaken, and that will create a warming in the SST pattern over the NTA region. Again, this is important. When there is a warm NTA SST, that is going to generate a La Nina-like scenario that is going to transform the pre-existing El Nino to a La Nina scenario in the summer monsoon season through a cross-basin teleconnection pattern. Now, this difference between the with melt and with melt experiment is clearly visible between these two simulations. Without melt, we don't see any such transformation. And with melt, we clearly see that the pre-existing El Nino has transformed into a La Nina-like scenario. And this is also visible in the precipitation response. There is excess rainfall visible with melt as compared to the without melt. So this is just to summarize the entire mechanism, and these are the summaries. So basically, the take-home message would be the effect of Greenland melt is not just local; it is going to somehow impact the tropical circulation as well and impact the precipitation response there as well. Thank you very much. I would also like to thank Dr. Gunter for help with the experimental setup. Thank you very much. And I'm happy to take questions. Thank you.
Great. Thank you so much. That was very interesting. We've got a few minutes for questions. I'm going to stare awkwardly at you in the room for just a minute, and then I have one. All right. So I saw that your presentation focused mainly on the freshwater fluxes on the ocean currents. Do you feel like there might be atmospheric feedback due to changes in topography of the ice sheet under high melt scenarios?
I'm sorry, can you repeat it?
So under a high melt scenario, the topography of the ice sheet will change, and that could have an impact on the atmospheric blocking due to standing waves. Have you looked at that at all?
No, we haven't. But that's actually a very interesting approach. We can definitely check that.
All right, thank you.
Yeah.
Anything else? Okay. Thank you very much, Shashi. We'll move on to our next talk. Ahead of time. We're doing great. Ishraq Farouz from Princeton University. Are you there? There he is.
Yeah, let me share my screen.
Okay, we can hear you.
All right, can I take it from here?
Looks good. All right, 10
Perfect.
minutes.
All right, so hi everyone, I'm Farouz Ishraq, and I've been working on developing paleoclimate simulation capabilities for the community ice sheet model for the last year or so. This work is primarily motivated by paleoclimatic simulations of Antarctica, but it should also apply regardless of the region you're trying to simulate. Just to motivate this work a little bit, I always go back to looking at climate history in proxies, and one of the more useful aspects of being in this point in paleoclimate science is that there's a lot of work that has already been done. And so we have a really good idea through benthic records what the global temperature was doing for the last, at least for the last 5 million years. And then with even more precision, we have a better idea of what the temperature in Antarctica was through ice core records that go back roughly 800,000 years, but hopefully we can, using the Beyond Epica program, we're going to be able to extend it to 1.2 million years. But having these records means that there is a way for us to try to simulate Antarctica or any other ice sheet, but in this case, I'm going to talk about Antarctica, using these proxy records. And that is kind of the general theme of my presentation here. I will be talking about some schematics of updates to the community ice sheet model to go from a one-dimensional climate record like this to an actually forced ice sheet in the model domain. And there are a few steps to this, right? So one of the steps is to actually create the climate forcing. How do we go from a benthic stack or a time series of temperature values to 2D fields per given time step within CESM? So one of the ways that we have preferred to do this follows the work by Johannes Sutter in his 2019 and 2021 papers, which usually just takes a combined Epgadome C delta deuterium record and benthic stack and just scales it linearly scales it between 0 and 1, and then compares what these values would look like at different points in time in the climate record. For the present day values, the scaled climate index, or just the scaled climate temperature record, is roughly stands at 0.7, while the end members, which is the last interglacial and the last glacial maximum, stay on the two ends of like 0 and 1 in this scaled record. So now the way we want to create these intermediate temperature and precipitation states is to compare these climate index values from to present day or pre-industrial values. So if a climate index value is greater than 0.7, then it implies that the climate state was warmer than present day, but probably cooler than the last interglacial. And if it's smaller than 0.7, the opposite applies. Then the comparison happens between present day and the last glacial maximum. So that's kind of what we end up doing, is that we create these weighting, these linear interpolation weights that takes one GCM field from an ICSM simulation of, let's say, last interglacial, one GCM field of air temperature or precipitation from an ICSM simulation from the LGM, and then our best estimate for these values for present day or pre-industrial. And we're creating weighted sums that try to closely resemble what a 2D field would look like with as much of the details of our present day atmospheric features preserved as possible. And that means now we have roughly, let's say, every 100 years, a field of linearly interpolated temperatures and precipitation. But that's not enough to force an actual climate model. And this is another schematic, or another way to look at this, is that we're basically taking this benthic stack of temperature records, and then we're comparing them, scaling them between the last glacial maximum and the last interglacial over here. And the parts shaded in blue are where the interpolation is only happening between present day and the LGM, and the parts shaded in red are where the interpolation is only happening between the present day and the LIG. And that's kind of forms the basis of how we're generating intermediate time steps, intermediate 2D detailed fields of temperature and precipitation. But again, that's not enough. To go from having these temperature and precipitation values and actually forcing our ice sheet model, we need a way to convert these values to a surface mass balance. And there are many different ways of doing this, but because we're dealing with limited information and because we're working with paleoclimate results, the best really we can do is have estimates for air temperature and precipitation fields using our climate proxies. And that really gives us the only option it leaves us is to use a positive degree day model. And there's many different levels of complexity for the positive degree day model that just is like different variations of how you use a degree day factor to estimate melt. But the direction we're planning on going for now with CESM is to use the Califf-Greva positive degree day model itself, which instead of looking at the temperature, instead of just using a one-dimensional look at a temperature and saying that whether a given temperature in a year is above zero or above melting or not, we change the question to how much of the temperature distribution sits above freezing. So we're basically creating a roughly normal distribution, normal distribution of temperature values that are distribute themselves around a monthly mean for each air temperature and precipitation value. And then we're calculating how many different positive degree days exist based on that distribution. This lets us have, even when we have monthly values of temperature and precipitation fields, this lets us have a way to simulate daily variability in temperatures with just a very standard assumption that there should be we can assume a distribution exists around a monthly mean. And so using this and the Califf-Greva PD integral, which is semi-analytical, so we really don't have to do anything like a table lookup. We can basically just use the conjugate error function within Fortran. I believe we're using Fortran 2008 compiler. So the conjugate error function should be supported by itself within CESM. And so by using this PDD integral, we're recovering how many positive degree days exist in a month. And then we can take this positive degree days in a given month and multiply that with the degree day factor to get an estimate for melt. And then because we have a precipitation value, precipitation field, by comparing that to our temperature field for a given month, we can also get an understanding of how much actual rainfall is happening that's not snow, how much actual snowfall is happening that's not just rain. And in total, all of this gives us an estimate of subtracting the snowfall from a runoff from melt and giving us a rough surface mass balance for the month. And then we can add all of this together through a model year and get a surface mass balance estimate for the entire year at once. So the point of this module is that we're basically taking the surface mass balance estimate for each month, for each year, forcing the model for that entire year, and then recomputing a surface mass balance estimate for the next year. And the way of doing, the reason we're doing this on a monthly level instead of just doing an annual estimate is primarily because for Antarctica, lapse rates and winter inversions happen and they're not negligible. So we want to be able to correct for inversions with different lapse rate fields over a year, monthly lapse rate fields, before we calculate our surface mass balance values from these fields. That's a lot of details that I got into, but I still want to motivate why this is useful and why a paleoclimate simulation is useful. The primary reason that I'm doing this is to look at Antarctic blue ice areas where we've been able to recover ice cores as old as, and if not older than 6.7 million years, which is around 6 or 7 times older than the oldest continuous record we have. However, we don't really understand why these records exist on the edges of the ice sheet. All these blue ice areas are near coastal regions, and we're not sure why we can recover ice as old. The point is to be able to simulate the community ice sheet model transiently and
1 minute,
emulate.
please.
Yep. The plan is to be able to simulate these blue ice areas in CESM transiently and get an understanding for what is happening in the ice dynamics that leads us to these really old packets of ice. Previous work within CESM, and in this case, we're looking at a blue ice area called Allen Hills in Eastern Antarctica. In previous studies with blue ice areas, it has been revealed that blue ice areas, you really can't fully understand blue ice areas with just steady state models because they're not truly steady state. Trying to recover or reconstruct flow fields and age depth profiles in a blue ice area with steady state models results in either mismatches in age or mismatches in surface velocities. And the broadly held assumption is that that would be solved if we try to transiently simulate these blue ice areas. And the only way we can do that, because of how old the ice is by running these long paleoclimate simulations. And our hope is that by creating this capability within the community ice sheet model that often mirrors the work that has already been done in the parallel ice sheet model, we're able to take advantage of some things like the age tracer within CESM that is truly unique to the work, to the capabilities of CESM, and get a better understanding of how and why these blue ice areas exist and why they can trap ice as old as we can find. Thank you so much. I know this was a little bit rushed, but I want to still thank the efforts from my advisor, John Higgins, my advisor at NCAR, William Lipscomb, and Dan Amron, as well as the huge help and support that Gunter and Kate have been throughout this process. Thank you.
Thank you. Are there any questions? Oh, how do I see if there's questions online? No questions, okay. All right, Ishraq, if you have a minute, could you talk a little bit about some of the possible errors around precipitation that you might have with this technique?
Yeah, this is a little bit of a contentious topic. I will give you that. The best assumption that doesn't really take it too far that I found is just scaling the precipitation based on the temperature, the paleoclimate temperature that we reconstruct. So what we're basically saying is that temperature scales at a roughly constant, like precipitation scales at a roughly constant rate with temperature. And we're taking our present day precipitation field and then adding these scaled anomalies using the temperature reconstruction we have for a given point in our time series. And that is truly the farthest I'm comfortable going, especially with the fact that we're really not working with a lot in terms of paleoclimate records. So it's quite easy to make assumptions that don't hold. And so by only resorting to these really fundamental relationships that we can somewhat trust, we're trying to mitigate any like contamination in our results from like assumptions that we probably haven't thought of before.
Okay, thank you. Anybody else? All right, Betty. I got you. All right, we're a little behind. Sorry, I like questions. All right, you get notes here, and your slides are up there. And up and down, move you down.
Okay, so today I want to talk about kind kind of a paleo perspective on the Greenland ice sheet and the polar, but it's kind of a counterpart to another project that we're doing with TIPMIP called What If, and I'll talk about that, I guess, at 12:15 today, boreal forest experiment. So what we know today is that boreal shrubs and trees are expanding north and becoming stressed along their southern margins. We have some satellite measurements that the Arctic is greening. This shows measurements that show positive trends in the what's called the NDVI, or the Normalized Difference Vegetation Index, as an indicator of photosynthetic activity, in other words, the greening of the landscape. So you can see from looking at this, the one on the left is for an earlier trend, and the one on the right more recently, that the treeless tundra ecosystems of the circumpolar Arctic, in particular the northernmost parts of Canada, Russia, and Scandinavia, have been showing greening recently. So this initiative, called TIPMIP What If, is part of the Tipping Point Intermodal Comparison Experiment, and it's designed to run Earth system models, so coupled models, in scenarios where the tipping has already occurred in a component. In other case, it has happened rather than waiting for it to happen, and then looking at the responses. So in other words, we seek plausible storylines of extreme future outcomes, and then we assess the impacts. So for today, I want to discuss what past warm periods can tell us about the cascading impacts of boreal forest changes, and in particular, conclude and why it's important that we include these climate vegetation feedbacks in our models of future state of the Arctic. So the time period that I'm going to talk about is a fairly recent warm period. It's called the last interglacial, running from 130,000 to 116,000 years ago. And we have indications from sediments across the Arctic, in particular plant and pollen macrofossils, that the boreal forests actually extended to the Arctic coast along much of North America and Eurasia. And we have a number of other indicators also. Speleothems in Siberia caves indicate permafrost was absent during the last interglacial. Indicators that the Arctic was probably ice-free or near ice-free seasonally in the Arctic, and also indicators that the Greenland ice sheet was smaller than present, with substantial retreat along its southern sector at about 122,000 years ago. So to tie these together, we conducted some simulations with the CMIP-6 version of CESM2 at nominal 1-degree resolution, and we coupled it to the Greenland ice sheet CESM2 at 4 kilometers resolution. We forced it with the orbital insolation anomalies. In particular, there were strong orbitally induced insolation anomalies during the spring and summer months, greater than 50 watts per meter squared, from about 127 to about 124,000 years ago, and then declining. And we ran 2 experiments. In the first experiment, CESM2 default in the land model had prescribed vegetation at 1850 or pre-industrial. So you can see that on the top figure there. It's particularly looking, just in this case, in the Baffin Islands in northern Canada. The light green is low and high shrub tundra. The kind of olive is kind of this erect dwarf, and then the pink is prostrate. So tundra up there, northern. That's also the case if you look in Siberia also. But we know that from proxy records that the boreal forest did extend to the Arctic coast. And so we ran a second simulation. In this case, we used the Biome 4 equilibrium vegetation model and asynchronously coupled the CESM2 every 500 years. So the bottom figure shows you what that's vegetation looked like at 125,000 years ago. And you can see as compared to the top, now we have boreal forests, kind of this cold evergreen needle-leaf forest extending into actually Ellesmere and farther north in the Canadian archipelago, and also more kind of low or high shrub tundra in that region. So we can compare these two simulations to look at the effect of vegetation and why it needs to be included when we look at the responses to either warm past or warm future climates. So what is shown here is summer temperatures, and I show again on the left that Cape reconstruction. On the far right is the one where we just used the orbital insolation anomalies to force the model and left the vegetation at pre-industrial. And you do see some warming, you know, maybe about 2-3 degrees over northern Canada and northern Asia. But when we actually change the vegetation more appropriately using the biome model, now you see much greater warming, in particular in northern Canada, the Ellesmere Island, and even in northern Greenland, up to maybe 4 to 6 degrees warmer, which agrees better with the proxy records there. We can also look at sea ice, and I'll just back up for a minute just to think about vegetation. When you put trees versus tundra, that lowers the albedo, and trees also have evapotranspiration, so you have more water vapor in the atmosphere. So you have these two effects that are heating the Arctic. So then looking at, and back up just a second, if you look also at the Arctic Ocean, you see greater warming around the Arctic Ocean, around the continents there than you do when you just leave the vegetation pre-industrial. So showing now sea ice, the far right is the pre-industrial sea ice concentration in September. The middle one is when we leave the vegetation at its pre-industrial, and you can see we do have a reduction in the sea ice just with that orbital forcing. But then when we also include the effects of vegetation, you see much more significant retreat. Not quite ice-free, but near ice-free. There's a lot of records, a lot of uncertainties, but most of them suggest that at least seasonally, it was probably nearly ice-free during the last interglacial. And then finally, just looking at the Greenland ice sheet on these two simulations, what is shown here is the ice thickness of the Greenland ice sheet simulated by CESM2, going from the beginning of our simulation, 127,000 years ago, every 2,000 years ago to 119,000 years ago. And you can see the Greenland ice sheet is retreating due to both the orbital insolation anomalies and due to the fact that we now include the warming due to the vegetation changes. It reaches a minimum ice sheet extent just before 121,000 years ago, and it contributes 3 meters of sea level, global mean sea level. And this kind of concurs, there's some uncertainties with the ice sheet, but this kind of distribution that concurs with some of the records we have, in particular that the ice retreated in the southern and southwest Greenland that we have in marine records. When we don't include the boreal forests extending north and we keep the tundra up there, pre-industrial, then we see the ice sheet barely retreats, and in fact, it retreats, it gets its minimum at 124 and it starts regrowing. So its contribution to sea level is only 0.6 meters. So just in the summary, the model and data together from past warm periods suggest kind of this cascading impacts going from the boreal forest to sea ice and the Greenland ice sheet. And what it says is that we really need to represent vegetation in our land models. If we're going to look at them to look at predicting the future state of the Arctic. And I'm done.
Thank you. We could do one quick question, or we could move on and maybe you could talk to Betty at the break. Okay, thank you. Our next talk is Chloe Marie Pace at the VUB Belgium, and she's virtual. I see Chloe.
Hi, can you see and hear me?
I can see and hear you. I don't see
Okay.
slides yet.
Yeah. Can you?
That's better. Thank you,
Okay.
Chloe. 10 minutes.
Okay. Hi, everyone. Thanks a lot for having me as a speaker today. So I'm Chloe Pace, and as was already said, I'm a researcher at the University of Brussels and also linked to the University of Liège, both in Belgium. So as my title already gives away, I will be talking about the Greenland ice sheet and more specifically about the interactions between the ice sheet and the atmosphere. Because we will never get to see what the ice sheet will look like in 1,000 years or more from now, but we can make a guess. And I will show you today that to make a good guess, we need to include the interactions between the ice sheet and the atmosphere in our simulations. So what I've been doing is I've been coupling the MAR regional climate model to the Greenland ice sheet model, or GISM in short. And to assess the importance of the interactions between the ice sheet and the atmosphere, we've conducted 3 types of coupled simulations. One fully coupled one, wherein we include all the feedbacks between the ice sheet and the atmosphere. Then one wherein we only mimic the melt elevation feedback by applying an offline correction to the surface mass balance and the runoff. So a sort of spatially varying an annually recalculated lapse rate, let's say, for the surface mass balance and the runoff. And then the last simulation is one wherein we apply no corrections whatsoever and we don't take into account any kind of feedbacks. So the only simulation wherein MAR actually sees the ice sheet surface elevation changes from GISM is the one wherein we include all the feedbacks. So in that case, we annually update the topography in MAR according to the topography from GISM. Now, as MAR is a regional climate model, we of course also need a global climate model forcing, and for that we had applied IPSL output under SSP 5 8.5 because it was available at the time of setting up our coupling framework. And why SSP 5 8.5? Well, because we wanted to observe large changes over a relatively short time span, because the coupled simulations are very computationally expensive. So that's indeed a high warming scenario because over the Greenland domain, we observe about 15 degrees of warming by the year 2300 in our forcing. And then afterwards, we have extended our simulations by keeping the climate forcing constant by randomly sampling the last 50 years of forcing. And so we see that this leads to very different sea level contributions between our experiments over time, which indicates that the ice sheet atmosphere interactions have a clear impact on the ice sheet evolution. Now, to identify their importance and to see also what these interactions are, or what the most important ones are, we had a look at what's happening over time. And first of all, we had a look at what's happening by 2300. So what we see is that our simulation without feedbacks or interactions clearly underestimates sea level contribution by about 21% compared to the simulation with all the feedbacks. So this is more or less in line with previous findings. However, if we look at our one-way coupled or offline corrected simulation, we see surprisingly that it only underestimates the sea level contribution by 2%, more or less. So either that tells us that the offline correction is performing very well, or something else is happening. And we had a closer look, and what we see is that most of the ice mass loss difference between the simulations is concentrated near the ice sheet margin, which is what we expect. But what we did not expect to see is that we see more retreat in our offline corrected simulations near the margins compared to the one including all the feedbacks. And so diving deeper into all the different variables and data, we found out that this is linked to changes in winds and wind speeds. So what we see here over time is the difference between our two-way and one-way coupled simulations, or the simulation with all the feedbacks and the offline corrected one. And we see that the katabatic winds over the ice sheet are strengthening. So we get somewhat darker blue over time over the retreating ice sheet. And then around the ice sheet that is retreating, we see that the wind speeds are clearly declining because obviously there's no more katabatic winds as the ice sheet has retreated here. And also there is a decrease in barrier winds that bring warm air from over the tundra towards the ice sheet margin. And so this combined effect, increased katabatic winds bringing more cold air to the margin, and then decreased barrier winds bringing less warm air to the margin, actually leads to reduced melt in our fully coupled simulation. And that effect is not captured with our offline correction. So here again, you see the difference in surface mass balance between both simulations. And by 2200, we see that the surface mass balance is a bit more positive in our two-way coupled simulation, so we get less melt. And then actually by 2300 and afterwards, we see the pattern that we had expected to see in the first place, which is more melt near the ice sheet margin in our two-way coupled simulations. And that is not because these changes in wind speed stop, they actually persist. But other feedbacks, like the melt elevation feedback, are actually taking over and dominating the effect on melt. So then also, if we go back to our sea level contribution curve, we see clearly that after 2300, we get a much higher sea level contribution in our fully coupled simulation. So that tells us that positive feedbacks are now being more important. And also looking at the ice sheet geometry, we clearly see much larger differences now between the feedbacks, between the simulation, including all the feedbacks, and the ones wherein the topography in MAR was not updated annually. And by the end of 1000 years simulation, the ice sheet has almost entirely disappeared, let's say, in our fully coupled simulation because of the high enforcing and because of the positive feedbacks. Now, what are these positive feedbacks? So there are several, but the most important one is related to changes in precipitation. So what we see here is what we expect to see, namely that precipitation follows the retreating ice sheet margin and that we get more precipitation over the ice sheet interior. But when we look at the precipitation phase, we see that there is a clear decline in snowfall. So we get a much lower snow fraction over time. And so the increase in interior precipitation does actually not lead to increased accumulation. And even more so, the decrease in snowfall leads to a decrease in total precipitation as well. So we see that rainfall stays more or less constant after 2300, but the decrease in snowfall is mirrored in the total precipitation. Of course, you could argue that if you are looking at an ever-retreating ice mask, you will also observe an ever-retreating total amount of precipitation. But we also plotted this with the dotted lines for the fixed area of the initial ice mask. So going back to the previous slide, here you see the retreating ice mask in 2500, and the furthest outline is in fact the initial ice mask at the start of our simulations in 1990. And for this fixed area, we also see that precipitation decreases over time. So basically the air that used to precipitate snowfall onto the ice sheet is now passing over the area and no longer precipitating, not even as rainfall. So what should you take away from this? Well, that we have observed a negative feedback related to changing winds near the ice sheet margins that was not captured with our offline lapse rate correction. but that over time, nevertheless, it's the positive feedbacks that dominate the system, and that one of the most important positive feedbacks is related to a reduced snowfall and snow fraction. And so therefore, we really need to take into account the interactions between the ice sheet and the atmosphere in our simulations if we want to get a more realistic sea level contribution over time. So yeah, thank you very much, and let me know if you have any questions.
Thank you, Chloe. That talk helped answer one of my big questions. I think, unless somebody has a quick question, we're running behind, so I'm going to move on to Miran, who should be here. Thank you very much.
Thank you.
So, go here, and we're going to find this. Where is it? Here. No. Where are all the presentations? Over here. There you are. And then we'll start here. You can go up and down and move your slides. There. Thank you.
Thank you. We are going to continue with Greenland, but this time with a global model directly coupled to a Greenland icing model. And the questions I'm going to address here for a set of simulations and at the multi-century scale is which forcing level triggers high Greenland ice sheet mass loss and how. What is the effect of change in Greenland on the ocean circulation? And what is the effect of AMOC change on Greenland ice sheet change? So we are using CESM2 with the interactive Greenland ice sheet. Changes in the topography and the area are communicated to the atmosphere and the land, and freshwater fluxes are provided to the ocean. This is the forcing that so the forcing that we are gonna use several scenarios where we are increasing 1% CO2 per year until stabilization at 2 times 2.5, 3 times, this happens at year 110, 4 times, that happens at year 140. And this is for reference, I'm gonna align year 140 of all of the simulations with 2100 CE. And the motivation for that is that in SSP5, the forcing is more or less 4 times CO2 by 2100. So this was my criteria. So here you can see this blue line that is 2 times CO2 and a green line that is 4 times CO2. So you can see that SSP3 goes above 4 times CO2 and SSP5 goes like 8 times CO2. And if we are comparing with the new scenarios, more or less, we can match something like the 2.5 with the middle scenario and 3 times, 4 times with the highest scenario. Okay, so these are the results for global mean temperature. So let's see if I can point. Okay, so first we have increasing global mean temperature for 2 times, then the brown line is for 2.5, then we go pink is 3 times, and then this one is 4 times. Okay, so for all the simulations between 2100 and 2300, we are moving in the space between 2 Kelvin and 6 Kelvin, and we are only exceeding 6 Kelvin in the 4 times CO2. Okay, now if we look at the AMOC here, so we have a similar decline for all runs, but 2 times CO2. 2 times CO2. Sorry. Okay, so this is the trajectory for 2 times CO2, and all the others are 4 times CO2, and even we have a one-way couple simulation where the freshwater fluxes to the ocean are prescribed as pre-industrial, and the evolution of the AMOC index is extremely similar. So we have similar decline whether we have pre-industrial melt from Greenland or we actually couple with the much increased melt from Greenland, so which is indicating that by the time we have built up, so that Greenland has built up a substantial mass loss, the other forcings from the atmosphere, the other freshwater forcing from the atmosphere and the warming have acted already. We can see that in the 2 times CO2 simulation, the purple line, from year 500 and 600, we have a recovery of the AMOC, and this goes together with an increase of 2 degrees in global mean temperature. We also have this simulation with an overshoot of the AMOC because we are drawing CO2 from the atmosphere very, very quickly. Okay, so these are the projections for the forest scenarios plus SSP5 by 2300. So we have in between 15 centimeters and more than 1 meter of range of sea level rise by 2300. And if we look at the ice discharge, it is declining in all simulations, much more for 4 times CO2, as it is becoming land terminating. At the margin, land terminating. And then if we look at the SMB, we are going to focus first in the differences between 2 times CO2 and 4 times CO2. So in 2 times CO2, at some point, the CO2, the SMB keeps in a positive, in the positive part, but the CO2 before 21, the SMB before 2100 is becoming negative in 4 times CO2 and declines very, very quickly. So we are going to look at maps, and we are comparing the SMB with respect to pre-industrial. And so for the 2 times CO2 pattern, we are going to look at the composition in snowfall and melt. So what we are seeing is that we have a decrease in snowfall that is explained by the decline in the AMOC. And we also have melt increases. They are modest, and they together explain this pattern. Meanwhile, in the 4 times CO2, we see this pattern of increased snowfall in the interior and much increased melt at low elevations and large expansion of the ablation area. Okay, and now we are gonna look at the other 2 scenarios, so 2.5 and 3 times. And we see something in between 2 times and 4 times pattern. So still in 2.5, we can see this footprint of less snowfall in parts of the interior, but much less than in 2 times CO2. And then 3 times is approaching 4 times pattern, but by very modestly. Okay. And now we are going to add SSP5. So we have a mass loss of 3.5 meters of sea level equivalent. This is a lot. But however, CESM2, we know it is biased for this very high forcing. So this is not realistic, the amount of response that we are getting. And also the projection of the SSP projection is not realistic anymore. It is not in the range that is going to be considered. So we are going to consider this non-plausible scenario as a tool to explore a transition to hyper-high melt regime. So it's like a theoretical tool. So what is going on? By comparison with 4 times the CO2, we have this very, very, very strong decline in the SMB in connection with rapid expansion of the ablation area up to the summit by 2200, and the amount of melt even increases in the following century. If we are looking at the 2 times CO2 beyond 2300, by the time of the recovery, what we are going to see is a profound reorganization in the SMB forcing to the ice sheet. And so if you compare this anomaly by GR 400, now we are in model years. And then later, we are coming to the pattern of 3 times or so, but later in 2 times CO2. If we look at the time series here, so because we are accelerating the ice sheet from GR 500, this 100 years of recovery of the ocean translate on 500 years of simulation for the ice sheet. 1 minute. Okay, and in this time the SMB becomes negative, and so by year after 3,000 years we have 4-meter sea level rise. Okay, so these are the main results. There are large differences between 4 times and 3 times because we have this large acceleration of melt by year 120. We have a large effect of the AMOC on the ice sheet, but we don't see the opposite effect. Yeah.
I'm going to give quick space for a question if there is one. If not, take Mira in and talk to her at the break. Thank you. Our next talk is online. Oh, no. Pran Kumar, are you here? Wonderful. Come on up. Our next talk is Pran Kumar Tripud from the University of Delaware. Let me find your slides. Perfect. And then we'll go up all the way. Okay. And up and down, maybe back.
Can I use the intro? Awesome. Good morning, everyone. My name is Pranay. I'm a 3rd-year PhD student at the University of Delaware. First of all, I would like to thank to my advisor, Chandana, and Department of Earth Science, University of Delaware, and UD Climate Hub for sponsoring my visit to NCAR. And also, so much thank you to Gunther and Bill for having me here do this research. So I'm going to take you back to Paleo and Southern Ocean, and we're going to talk about some icebergs. So my topic is linking Southern Ocean ice-rafted debris flux to Antarctic ice sheet dynamics. So Antarctica loses ice in multiple ways, one of which is basal melting and also iceberg calving, latter which account for more than half of the ice mass loss from Antarctica. Now, whenever these icebergs they break off through this ice sheet, they also carry sediments that were eroded by the glaciers. And as they move and drift along the way out in the Southern Ocean, they melt and they deposit all these sediments on the ocean floor. Now we can use these sediments, so-called ice-rafted debris or IRD, to study past ice sheet iceberg discharge and hence ice sheet dynamics. But the thing is, IRD has traditionally been used to infer Antarctic ice sheet evolution. Mostly, you must be knowing about the Eocene-Oligocene transition, where you have first occurrence of ice sheets reaching the oceans, and also Heinrich events in the North Atlantic. Open ocean records are really difficult to interpret, because a peak in IRD flux does not necessarily mean ice sheet expansion or retreat. It could also reflect changes in transport pathways or iceberg survival. Now, that's why we need high-resolution IRD records from the open ocean. We have one from IODP site U1539, which is in the Central South Pacific sector over here, which has very high sedimentation rate, and the oldest age is going back to 1.4 million years. We go out there, we drill through these sediment cores, and we have over hundreds of meters of long sediment cores. And as you can see in this picture, it's mostly mud dominated, but when we zoom in, we also see these huge debris or rocks, which we can identify using X-ray images. Some of them are not visible entirely just by looking at the mud. You can see them in the X-ray images. And we can train machine learning models to identify and count these rocks or IRDs to generate a flux record of ice-rafted debris. I'm going to take you to results. So what you're looking at are different records from the Southern Ocean. It's really hard to get continuous records from same site or nearby sites. So what I'm going to be using is ice volume record from a site called 1123, which is over here, and which is this one, and then sea surface temperature from an ODP site 1090, and ACC strength, which was reconstructed from very close to this site, U1540. I'm going to orient you in time. So we are 1400 kiloyears on the right side and going towards the modern, towards the left side. And you can see 1.2 million years to 750 kiloyears is the mid-Pleistocene transition. In the older part of the IRD record, we don't see a lot of IRD coming in, but after the mid-Pleistocene transition, there's a lot of IRD coming in, and especially it inclines with the ice volume increase. So the value is going down over here. That means it's a glacial period, and we see peaks during glacial periods. The gray bars are not visible. Sorry. But we also see that the cold temperature favors iceberg survival, and we have more IRD coming in. Also, whenever the ACC strength, Antarctic circumpolar current strength, when there's decrease in Antarctic circumpolar current strength, we also see peaks in IRDs. So what does that mean? It's really difficult to interpret. So I'm going to be using a modeling framework using CESM and iceberg drift and decay model called as PIBER. So CESM is going to simulate Antarctic ice sheet evolution, great ways to estimate calving flux and iceberg production. And we're going to use the data from CESM, feed into the model called PIBER, which reads monthly climate forcing, and it can simulate iceberg drift and melting under ocean currents, winds, and it has published and established iceberg dynamics. And previous studies have shown that it can mimic, or it shows a general good agreement with the modern iceberg trajectories. So these are modern iceberg trajectories and reconstructed with using PIBER. And this model has also been used in the late Pleistocene studies as well. So this is where linking models to sediment records comes into the picture. So we're going to run CESM under different climate states, such as PEI, LGM, and LIWG. These are going to be your baseline condition. And then we're going to generate iceberg discharge scenarios and simulate iceberg trajectories with PIBER and calculate iceberg arrival at site U1539, which is in the Central South Pacific. And they're going to compare modeled iceberg flux with the observed IRD flux. And this is going to tell us which Antarctic sectors contribute IRD to site U1539. And what is the provenance of rocks coming in to that sector. Further down the line, we're also going to dissolve these rocks, and using isotopes such as neodymium, strontium, and lead, we're going to pinpoint the exact locations from where they came from or which Antarctic sector they came from. And then we're going to study how sensitive is IRD delivery to the ocean circulation, which is the dominant factor driving these icebergs out in the open ocean. And can model iceberg fluxes reproduce observed IRD peaks, and under what conditions? So these are conclusions and my future visions. So IRD provides a valuable proxy for the past Antarctic iceberg discharge, and combining ocean sediment records with CESM and PyBerg enables process-based interpretation of high-resolution IRD records. And model data integration can identify potential source regions and mechanisms driving IRD variability. And down the line, if PyBerg combined with CESM explain IRD in the Central South Pacific, the output from the PyBerg can be used potentially in the ocean model MOM to simulate iceberg trajectories in CESM and improve solid meltwater distribution over the Southern Ocean. Thank you so much. Happy to take questions.
Thank you very much. Hi, Dave.
This is pretty exciting. Do you have interaction with sea ice in this iceberg model?
Yes, we do.
Okay.
So yeah, this is an offline model. So you can, it takes inputs such as wind forcing, sea ice concentration, sea ice thickness, and ocean, a lot of data from that. But the icebergs, the melt does not interact with any other components. Yeah. Yeah, the icebergs can get stranded in the sea ice if it exceeds certain percentage.
And then I have a follow-on that you're talking about the flux of meltwater. Would this be a static forcing that we would add online, or are you talking about computing it on the fly?
I think it's as icebergs drift, the melting and the meltwater is calculated as they're melting. So you do get a gridded output of meltwater. Yeah.
Cool.
Thank you.
Who is it, Caroline? Wonderful. Okay. So it looks like our next talk is not online currently, unless somebody wants to jump in here real quick. So we're going to move on to Caroline Van Kalsar from Delft University, who's giving a remote talk. Caroline, are you there? Maybe.
Hi, I'm here. Can you...
Okay, we can hear you, but we can't quite see you, and I don't see any slides yet.
Okay, I can't get my video to work.
Oh, okay, Caroline, so it sounds like there's a little bit of technical difficulties. We're going to move on to our next in-person presenter, who is Bill Lipscomb. So Bill, why don't you come on up, and we'll get you figured out, and you can talk after, Bill. Okay, so your talk is here. And, oh, for this one, I have to do this, and then this, and then you're good.
Advance with. Okay, I'm going to talk a little bit about the upcoming ISMIP-7 experiments and our CESM participation with those experiments. So to begin with, we're about to release a new version of CESM, version 3.0, along with CESM3. Since version 2, we've done a lot of work on the model. The dynamical core is pretty similar, but a lot of the physics has been changed and improved, including calving algorithms and calving laws, and new ways of approaching basal sliding, subglacial hydrology, inverting the model. We can now use CESM for glaciers as well as ice sheet simulations. And we're in the process of linking CESM to the fast isostasy model so that we have a better GIA component, glacial isostatic adjustment for CESM. For coupled runs, we now support multiple interactive ice sheets, so you can run Greenland, Antarctica in the same simulation, and a number of new diagnostic and testing tools. And ISMIP-7 is the ice sheet model intercomparison project for CMIP-7, the successor to ISMIP-6. ISMIP-7 aims to produce consensus estimates of sea level rise from ice sheet contributions. We're on a tight timetable because of the AR7 deadlines. ISMIP-7 has two main components: standalone ice sheet simulations forced by output from Earth system models and coupled Earth system simulations with interactive ice sheets. The ESM simulations are on the slower track, and we'll talk about those maybe next year. But for now, the focus is on standalone simulations, the results of which are due at the end of September. Since ISMIP-6, there's been some shifts in the emphasis of ISMIP. One thing is that the ISMIP-6 simulations generally stopped at 2100. Just as many interesting things are beginning to happen in the simulations. So for ISMIP-7, we're going to go farther, typically to 2300. There's more emphasis on matching observed changes from the historical record as a way of making sure we have a realistic sensitivity of our ice sheet models. And also, in addition to kind of the standard Tier 1 experiments, groups are encouraged to do a lot of optional experiments where they explore different ice sheet physics and climate forcing to get a better sense of the true uncertainties that we're looking at. The Greenland experiments are a little bit different in that we have parameterizations for frontal melting instead of that simply being prescribed. And in Antarctica, there's a fairly involved procedure for calibrating your subshelf melt rates so that they're in good agreement with observations and more sophisticated high-resolution models. So calibrate those melt rates before you run them into the future. And we're in the process of doing that now. This is a plot on the right from work by Tim Bondenacker et al. And published last year. In these simulations, the model is initialized in such a way that when the forward simulation starts, you reproduce the present day melt rates. And then you just let that go with no additional ocean warming. And we find in those experiments that you generally have a few centuries of slow retreat, and then you reach a threshold where you have rapid and probably irreversible collapse happening on a time scale of 2 or 3 centuries. The collapse time scale seems to be independent of the details of the forcing. These runs use a fairly simple calving mask. What we do is we simply prescribe the calving, the ice sheet, floating ice extent not to go beyond present day observations. So we have a mask to cut off any ice that wants to go beyond the present day ice sheet. But then when the ice sheet retreats, the ice front generally stays at the present day value, even as the ice thins, unless the ice goes away entirely. We think this is not very realistic because we're preserving large ice shelves, which provide significant buttressing, where in reality, probably there would be some thinning and retreat of the calving front, which would reduce buttressing and lead to additional retreat. So we want to do some experiments where we allow this retreat to happen and see how much it might increase the sensitivity of the ice sheet to warming. So in the interest of time, I'm just going to describe one set of experiments, which is something we'd like to do for ISMIP-7, which is swapping out our calving mask for a physically based calving scheme. I won't go through the details of the run, but just to describe the calving, sort of the control experiments, you have this calving mask based on present day. And then the more physically based experiment is we include a calving law where the calving adjusts to 2 things. One is the ice thickness. There's a critical ice thickness below which calving starts to happen. And also there's a stress threshold above which the internal ice stresses drive increased calving. And we want to make sure we have a reasonable calving law and to tune our parameters. We want to compare the present day calving fronts with observations. And to the extent those are accurate, then we can perhaps trust what's going to happen in the future. And so for the experiments, we simply spin up the model to steady state, which you can think of as like a pre-industrial spin up. And then we apply uniform warming in the Amundsen Basin only, where Pine Island Thwaites glaciers are located. And the warming is relative to PI, so think of this as warming that to some extent has already happened and is committed. So the spin up, on the left-hand plot, you can see at continental scale changes in the ice sheet calving front. Blue indicates retreat and sort of green turquoise indicates advance. On the left-hand plot, you can see the Rani ice shelf in the upper left has advanced a bit. Several ice shelves have retreated, at least modestly, but on the whole, this is pretty good for a calving law that only has 2 adjustable parameters. And on the right, you can see the Amundsen Sea embayment looks a little different with some general expansion of the Pine Island Thwaites shelves, but still not so different from present day. So that gives us some confidence that our calving law is not way off base. So then we do these warming experiments, and this plot shows time series from year 2000 at the start out to year 4000. And there are 4 lines in each plot, a control experiment with no warming, and then experiments with 0.5, 1.0, and 2.0 degrees of warming. So start with 0.5, which is green. In the top plot, you can see that there's virtually no response from half a degree of warming with the observed calving mass. In the bottom plot, it takes a while, but somewhere after year 3000, we have this collapse of Thwaites Glacier. And then if you look at 1 degree, which is the red line, in the top plot, you have collapse beginning around 3000, and the lower plot, you have collapse beginning shortly after 2500. So the calving law feedbacks moves the collapse period upward, and that's also true with the larger amount of warming. And the way this unfolds is the colored contours here show the retreat of the grounding line in the Amundsen Sea embayment, where you can see the very deep trough that Thwaites Glacier sits in, and then the somewhat smaller, narrower trough extending this way, which Pine Island sits in. You can see that with the calving mask, the grounding line stays put for longer. So for example, if you look at the orange line at year 2800, in the left plot, you've had just a little bit of grounding line retreat at that point, whereas in the right plot, the orange line is way back, and you've had a collapse of Thwaites Glacier at that point. And similarly, the patterns are similar either way, but everything happens earlier when you have the calving feedback, which reduces the buttressing and allows things to proceed more quickly. So just to summarize, we're now in the midst of running standalone ice sheet experiments for ISMIP 7 with coupled Earth system modeling experiments to follow after that in the next year or so. Our emphasis is on including more realistic processes. Here I've talked about calving, but we also want to do experiments where we have more realistic basal sliding and subglacial hydrology, also incorporating isostasy, which typically is a negative feedback on ice sheet retreat. And in this talk, we show that with a more physically based calving law, we have positive feedbacks that make the collapse of Thwaites Glacier and Pine Island glaciers more imminent, which is obviously of concern if we're thinking about we may already be past thresholds that we need to somehow go back to earlier cooler conditions. And then the question is, how long do we have to do that before tipping the system into an unstable state that would raise sea level by at least 1 to 2 meters? Okay, thanks.
Do we have any questions in the room? Do we have the other 2 talks? Okay, Caroline, are you around?
Yes, I am here. Can you hear me?
Oh, yes, that's much better.
Great. Let me share my screen.
Oh, and we can see you. That's great.
Yeah. I just cannot click the share now. Yeah, it's working. The share.
Nice. All right, our next talk is Caroline Van Kelsar from Delft University.
Hi, everyone. Thank you. Thanks for the opportunity to join online. I will be talking about the interactions between the Antarctic ice sheet and the solid Earth, and I will mention a little bit about Greenland later. The most important interaction between the ice sheet dynamics and the solid Earth deformation works via the grounding line. So here you see the ice sheet from the side in green and the grounding line in brown underneath and the sea level in blue. So the grounding line is where the ice touched the bedrock underneath at point P1. But when the ice melts, here you can see it in the dashed line, there is less mass resting on the Earth's surface, and this causes deformation up to 600 kilometers deep inside the Earth, moving the bedrock surface upwards. So when the ice retreats, the grounding line retreats to position P, but now when the bedrock moves up, the brown dashed line, you can see that the new grounding line position is more advanced towards the ocean. And this is therefore a negative feedback. So the solid Earth deformation is stabilizing the ice sheet. Also, it brings the top of the ice sheet a little bit more in a colder atmosphere. And it decreases a little bit the water depth beneath the ice shelf. So there's also a local effect because of the decrease in gravitational pull from the ice sheet to the ocean. The sea level decreases in the near field of the ice sheet and increases in the far field. So the question was, how much will the Antarctic ice sheet be affected by solid Earth deformation in the coming 500 years? So when we go deeper into the structure of the Earth, you can see here the viscosity, which is the main component that determines how easy the Earth deforms. So you can see at 3 different depths of the Earth, for example, at 70 kilometer depth, you can see there's lighter colors close to the grounding line in West Antarctica, and the viscosity is about 10 to the power of 20 or 10 to the power of 21 Pascal seconds, which is relatively low. Also at 250 kilometer depth, you can see there's a big difference between East and West Antarctica. So this corresponds to a certain response time. When it's very low, like 10 to the power of 18, the response times can be as low as 50 years, whereas when it's higher in East Antarctica, it's about 150,000 years. So the fact that there is this low viscosity regions in West Antarctica, we can suspect that there is an effect of the solid Earth also in the coming centuries and not just over very long time scales. So the important part to remember is the lower the viscosity, the faster the response and the less ice melts. So we used a GIA model to compute the deformation in the coming 500 years. We used seismic observations to obtain the mantle temperature, and then together with the stresses from the change of the ice and the grain size of the mantle material and the water content in the mantle of the Earth, we compute the deformation and the strain rate. So we coupled that GIA model to EMAU ice and computed the next 500 years based on 2 different scenarios, SSP 1 2.6 and SSP 5 8.5. And we used 2 different GCMs, the CESM 2 and IPSL model. So here you can see how the mean ocean temperature anomaly around Antarctica is over time. And so we use these simulations from CMIP 6 up to 2300, and then afterwards we kept it constant in time. So this is for the IPSL scenario in the low emission scenario. And in this case, there was strong warming of the Amundsen Sea, and we see therefore a strong retreat in the Amundsen Sea embayment. So here in red, you see the grounding line retreat when there is a rigid Earth, so there's no deformation included. And the green line shows when you include this 3D Earth structure that is stabilizing the ice sheet. So the grounding line is retreated less, with about 750 kilometers in the year 2500. And there's a big difference in ice thickness, up to 1500 meters. And there's a difference in bedrock elevation. So over these hundreds of years, the bedrock has uplifted with about 150 meters. So it's very, very rapid uplift. So the grounding line retreat is therefore delayed by 50 to 130 years. So what does that mean for the global mean sea level, this barostatic sea level contribution? You see that here over time. And when you look, for example, at the green lines again, and that's the low emission scenario, and then the light green lines are the CESM GCM and the forcing, and the dark green lines are from the IPSL forcing. So when you look at the dark green dash line, it's the rigid IPSL. And now the solid line, dark green, is the 3D IPSL. So it's significantly reduced the sea level contribution when you include 3D GIA with about 20%. And you can also see that the dark green dash line, which is the rigid IPSL, is at the same location more or less as the 3D CESM. And that means that the effect of GIA, of bedrock deformation, can be as large as the uncertainty between the two GCMs, so the CESM and the IPSL forcing. So this shows us that it's a big effect over time, and our new results show already this effect in 2300 and not only in 2500. So also for 2300, this is already relevant to take into account. Still, I want to emphasize that, of course, the emission scenario is the largest uncertainty. And that GIA plays a bigger role when retreat occurs in the Amundsen Sea embayment. When you use the CESM model as forcing, there's stronger warming in the Weddell Sea, and therefore there's stronger retreat from the Filsner-Ross ice shelf. And that's a different rheology of the Earth beneath. So therefore it matters which GCM you force the ice sheet model with, where the melt take place, and therefore what is the effect of the solid Earth deformation. So the next question we wanted to answer was, can we approach the effect of a 3D Earth structure on sea level rise using simpler models? Because the 3D deformation model is really computationally heavy. So we use these different Earth structures for the projections. We had the different 3D versions. We have the 1D Earth model, and we have LRA, which is a 2-layer flat Earth with a uniform relaxation time of the relaxed astenosphere, is called. It's sort of an approximation of the mantle. And that is 3,000 years, but that's usually used as 3,000 years. But as we already saw before, the viscosity in West Antarctica is so low that the response time can be 50 years. So we wanted to test what the parameter of the uniform relaxation time actually does and how it approximates the 3D model. So here you can see again the barostatic sea level contribution over time. And the black line is the contribution to sea level when you use that simplified LRA model with a relaxation time of 3,000 years. This is nearly the same as using no deformation at all. So I didn't plot that line because they are basically overlapping. So we found that using this such a large relaxation time did not impact the ice sheet at all. Then the pink and the orange lines are the contribution when you use the two different 3D Earth structures. And you can see the gray, which is a ensemble of different relaxation times between 200 and 500 years, so much shorter than the 3000 years. And you can see in the low emission scenario, which are the solid lines, the gray ensemble quite well matches the two 3D Earth structures. So this means that when you use a shorter relaxation time for LRA, and we advise to use 300, you can relatively well approximate a 3D Earth model. But for the high emission scenario, this is much harder over longer time scales. The uniform relaxation time doesn't work so well. So it's a relaxation time of 3000 years is overestimating the sea level rise. This I'm gonna leave it for later. But if you
1 minute, Caroline.
Okay. If you use about 350 years, you're already approximating it quite well for the low emission scenario. Then the last slide. So here, this is where we tested a laterally varying relaxation time. So there was never an equation to compute a relaxation time from the viscosity, but we derived this equation empirically by running a lot of simulations and computing the relaxation times for different regions. And we came up with these maps. So we found that one of these maps we're actually working really well. This means that an ice sheet modeler doesn't need to change anything in the LRA model. You just read this 2D 2D file basically, and use that instead of a uniform relaxation time for this layer of the Earth. And then you already include much better the sea level contribution. So here you see the deviation. The 0 is exactly the mean, the average between the two 3D models in pink and orange. So when it's 0, it's perfect. And you can see that the dashed brown line is one variation of these maps, which work really well. So we found that using this map from the 2D lower bound on the right hand side actually approximates it almost perfectly, the 3D model. So we advise to use this 2D relaxation time maps instead of a uniform relaxation time to improve your approximation of the solid Earth. So it means that 3D solid Earth reduces sea level rise by 9 to 23% in 2500, but actually already in 2300. And it delays the ice sheet retreat by 50 to 130 years. And you can approach it preferably with a laterally varying relaxation time for your LRA model. Thank you.
Thank you. Okay, Gunter, go ahead.
Hi, Caroline. Thanks for the talk. It was great. Maybe I missed it, but in your ice sheet model response, do you include the change in sea level as well?
Yeah, so we tested with and without, and we found that the sea level, just by the decrease of gravitational pull to the sea level decreases by 8 meters in 2500, but the bedrock uplift is about 150 meters. So this effect of the gravity is there, but it's actually quite small compared to how much the bedrock will rise. So it's a small, it turns out to be a small component.
Thank you. Do we have our other talk online? All right, wonderful. I think, Taco, are you there?
Thank you.
Great.
I'm here.
All right, we're going to circle back to Taco Brose for Delft University for the final talk.
Okay, thank you. Let me put up my presentation. Am I now sharing my screen, and is it now visible in presentation mode?
Yes, looks great.
Okay, thank you. Yeah, so I'm doing this work together with Mike Isabout and some colleagues from KU Leuven and Bert Wouters and Jan Wuiten. We're actually looking at how damage modulates calving, now specifically of the Pine Island Glacier. This is some older work from Steph Lermite, where you can see that there's different types of damage in the Pine Island Glacier over the last few years. Blue lines or blue arrows show mostly shear-related damage, so where there's not so much of an opening, and the green arrows point at extensional fractures and crevasses, so where there's an area increase or opening of the ice sheet. And in this talk, I will go over what's the effect of this type of, especially the extensional crevasses and fractures. What's the effect we think on calving? So our hypothesis is that it's mostly damage outside the ice tongue that initiates fracture by changing the moment balance on the outer end of the ice tongue, and eventually leads to calving. What we're using is a Sentinel-1 observation, C-band, and we're using the product from Jan Wuiten et al. That they produced, so ice velocities for the full of Antarctica, and we're looking specifically at the Pine Island Glacier. So we're looking into what we use. So the product is incremental displacements. So here in the X direction and the Y direction, and we use these these are in Eulerian, so these are in a space-based frame. And what we do is we go from Eulerian to Lagrangian, so to follow actually particles of the ice. And here I show what this does. So we recreate the particle path, and we can actually look at the cumulative deformation of the ice over time by recreating the particle path of an initial grid. By looking at then, if we have the Lagrangian velocities, we can also look at the cumulative deformation. So we derive the cumulative deformation here you see from beginning of 2017 up to end of 2022. You can see deformation, the cumulative deformation steadily increasing, and you can also see some calving events. You see nicely the Pine Island Glacier tongue. You can see the two bounding shear zones, but you can also see quite some damage and deformation in the rest of the ice sheet. So we derive strains, cumulative strains, and what we do, we look at the principal strains, and by looking more or less at the ratio between these two strains, these principal strains, we can classify the type of deformation going in blue. That's area increase, so extension in two directions, to extension in one direction, to shearing, where both principal strains are have more or less the same size but are different in sign. But we can also in reddish you will see the area decrease, so shortening in one or two directions. And it's mostly important, the area increase, we think is most important for understanding the type of damage that may lead to calving, because it allows for opening if we have area increase, and especially discontinuity. So if there's fracturing of the ice, this may reduce the ability of transferring stress from the ice tongue to the neighboring, the rest of the ice sheet. So what we do, and here I use, sorry for this, a slightly different color code, but it's in principle the same analysis of the principal strains. where green is pure shear, blue is extension, and sometimes we also have some shortening that's pinkish, and it's a continuous scale. So if there's a bit of shear and a bit of extension as well, so then it is somewhere, the color is somewhere in between. So we can actually look at the type of deformation and whether this is pure shear or the shear also contains an opening component. So again, this is over time. We start in 2017. Blue, you can see opening leading to calving, but you can also see that most of the shear zones are green, so are purely shear, but sometimes they're a bit more blue, which means that there's, if you look at the SAR images, there's fracturing, but there's also means there's area increase, so there's opening. And you can, we have looked at 4 calving episodes in this period, and you can see both the strain analysis that I did, as well as the SAR at the right. And then we can see more or less 4 calving events, but also we can see damage to the right of the image, which is the south, where there's quite some opening, fracturing and fragmenting of the ice, which correlates to more blue areas compared to the green areas. Green is pure shear, but the more blue is denotes partially extension. So for the first episode that happened in 2017, what we see is that there's an initial, here in the blue, you can see the start of the fracturing and calving. And at the same time, we see in this damaged area, we see that there's opening. So we can see outside of the ice tongue itself, we see that the shear zone includes opening. And that's nicely visible in this part of the image. So we can see that after the calving, we can see that the part where the calving more or less started is adjacent to areas where there's quite some extensional deformation. If we zoom in, we can see that here's in the beginning of the rupture that opens, we can see that it more or less aligns with the area where there's in the shear zone is opening, namely blue areas. And this is a step further away towards the end of right before the calving event happened. There's a second calving episode, and we can open the videos, and we can see that again, the calving more or less started in an area where there was quite some opening. If we zoom in, this is more or less the first month where we see opening, and we can see that it aligns with an area in the shear zone that has quite some damage. And in the SAR images, we see that this is based on this damage is accommodated by quite some fracturing. A third episode in 2020, we can see again here with the black arrows, there's an area with a lot of damage. Here you can see it with a blue color. And when we start the video again, we can see that the area that where the calving starts is more or less the area where there's also opening in the shear zone. So here you see in blue the developing the start of the rupture, and it aligns with an area where there's damage. And for the last episode, we see again damage here at this side. We actually never see until 2023. You never see damage in the northern shear zone. It's always damage in the southern shear zone, and that's also more or less the areas where the rupture is starting. So here you can again see there's a damaged area. We can see it here in bluish and here in the SAR images as fractured ice. And this is again the location where the damage is starting and the rupture is starting. And this is a zoom in. And sometimes we also see some shortening, meaning there's a compression. And we think this happens because there's fractures, fractured ice that starts to rotate and sometimes becomes too big for the channel in which it moves, and then got stuck. So our mechanical conceptual model is that these shear zones actually lead to or can accommodate tractions to the opposite to the direction of flow. The blue arrows denote the gravitational potential energy that drags the ice towards the ocean. And in the state from 2015 to 2018, there's the southwest tributary that also flows into the ice tongue. But we see that, and this is, we think that this is sort of balanced, but what happens But as soon as we see more or less fracturing in this southwest tributary, there will be less possibility for tractions between the ice tongue itself and its surroundings. What we then think what happens is that the tensional stresses at the area where there are less tractions that oppose the motion, the tensional shears will be, or the tensional stresses will be larger. And that's why we think most of the calving starts here. And this is this only becoming stronger, this effect, at the moment when the end of the south of the tributary has been lost because of calving, and there's more fracturing. So only at the northern side, so here at the left, there's still tractions, which means that there is a moment imbalance, and this has to be counteracted by larger tensional stresses towards this direction. So which means that we always see calving events starting from this side on. What happens in the end is that from 2023 on, is that also the northern shear zone is also damaging more, and we reach a sort of a new state again where the tractions at both sides of the end of the ice tongue are lost. So actually there's a free flow, there's no buttressing anymore in this area, and until the newest SAR images that I've seen still do not show any signs of rupturing, so there's a new balance. And the fact that there's likely a moment imbalance we can also see by rotations. At the left I show the magnitude of velocities, at the right the azimuth of the velocities. And we can see towards when there's a new rupturing, a new calving event, that we get a clockwise motion, which shows that there's also a clockwise moment imbalance. I'll show it again. We
1 minute,
see that
please.
the azimuth is different. So 1 minute?
Yes.
Okay, so my conclusions is that the asymmetry we see, it always leads to calving, asymmetry in the damage on both sides of the ice tongue. The calving always initiates in locations of extensional damage. And as soon as we have symmetric damage at both sides, we are entering a period without calving. Our interpretation is that the damage modulates the amount of shear tractions at both sides of the ice tongue, and this likely leads to local peaks in stresses. And then my speculations is that, of course, this reduction in shear tractions likely speeds up the ice tongue more. And also, if we look from a modeling perspective, can we understand calving without understanding damage or modeling damage? And I think that it's rather than a spatial average of stresses that you sometimes see in literature, is rather the local peak in stress that is more important for understanding where calving is starting. And this may lead also to a positive feedback between speed up of the Pine Island Glacier and damage. So this damage is related to differences in velocities between the tongue and the rest of the shelf. So what will happen to the buttressing here? Will we see a loss of a large fraction of the buttressing? Thank you.
Thank you. All right, so unless there's one quick question jumping up. Oh, okay. Go ahead, Kevin.
Thanks. That's very interesting process studies and modeling. I'm wondering whether there's any interest in possibly forecasting with this model, and have you looked into data assimilation with the observations you have available?
Yeah, so this is not a model. This is fully data driven. So there's only an analysis of the data. So we also cannot do any forecasts. So it's only the SAR data, the velocities, and then the interpretation of the strain rates.
Okay, thanks.
Thank you.
All right, so we have a break, and then we'll return with the Paleoclimate Working Group at 10:45, please.
Clickers.
No, it's just gonna be the.
Okay, just those. Yep, that
These
sounds
guys,
fine.
yeah.
Cool, thank you.
That's right.
Did you realize that the stuff you had down there is all like the...
Oh, no. That's pretty funny stuff.
All right, I think it is 10:45, so we're going to go ahead and start the second part of our polar focused session. This one is more focused on the Polar Climate Working Group and sea ice components of the model. So we'll have a number of in-person presentations first, and then we'll have some remote ones, and we're going to end with a discussion. We showed the code of conduct at the very beginning, but I just want to remind everybody to do all the normal things, share the air, ask questions, politely, all those sorts of things. And then if you do have a question, the mic in the center of the room, please ask it there so that people online can hear. So our first presentation is by Dave Bailey, and it's about the sea ice in CESM 3.
Hi. So I just noticed somehow the template, I left all the Latin down in the lower part. It loosely translates as, this is a picture of Dave standing in a melt pond. So anyway, so I think most of you have seen this sort of image before in presentations that I've given. And this is just the most up-to-date version of this. And so with CSM 3, so, CSM workshop, you are here. We've got 3 new main physics improvements that we've added in the sea ice component, which is size 6. 2 of which are brand new to size 6, the pond improvements and the flow size distribution wave interactions. And then there was a parameterization for a new congelation growth formulation from Mathieu Plante that was in size 6 and we just turned it on. So, and so then I'll show sort of the timeline that Dave showed, and but then in the future we're going to be adding more new physics, some more advanced snow physics. There's some machine learning advancements, which you'll hear a little bit about today. And then, as usual, the sort of long-term goal things are still being pushed further to the right every year. So the flow size distribution, Dave gave me a shout out. It's not 100% accurate, as I'll explain, but nonetheless, what happened in CSM2 was we had constant flow sizes. So every flow is just 300 meters. And then the waves didn't really see the sea ice at all. So they just kind of go to the sea ice edge and they just keep going. Now in the Northern Hemisphere, it wasn't bad because the wave grid stopped at 78 north. And so it didn't really touch a lot of the sea ice edge. But in the Southern Hemisphere, it was at 78 south. And so basically these waves were going all the way to the continent and then reflecting back in CSM2. What we've added in CSM3 is a more realistic flow size distribution, which gives you flow sizes of 12 different sort of bins. And then that actually will influence the wave attenuation within WaveWatch. And then that wave significant height, or more correctly, the spectrum from the waves comes back and then further influences the fracturing, the breaking of the flows. It increases lateral melt, and then you get more open water, and then more waves can sort of come in, and so there's this feedback going on due to the wave-ice interaction. So, as Dave mentioned, we had this problem in every version of CSM, CCSM since I've been here, and even before that, where the Labrador Sea would freeze over. And, sometimes it'll run fine in a pre-industrial run for like 100 years, then all of a sudden the Lab Sea freezes over. So, it can happen over these different time frames. There's also an element of sort of chaos here too, that, in the 30% of the runs we do, it doesn't freeze over, but then in the other 70% it does. And it's just a question of when it's going to freeze over. So, and then our traditional approach on this has been that, well, once it's frozen, it just sort of stays frozen, and we stop that run entirely. So, but based on a conversation I had with LIWG, CC Bits, and Marika, I decided, well, maybe I should just keep one of these runs with the full flow size distribution going. And lo and behold, like after about 60 years, it unfroze. And this is very atypical. We haven't seen this before in our other runs. And I mean, the physics, it's pretty complicated, but the main hypothesis is that because of this wave breaking, when the ice forms, it breaks up the flows, makes them very small, and then increases the lateral melt. And that really helps reduce the ice extent in the Lab Sea. But that's not 100% everything that's going on. The thing that Dave didn't mention yesterday is that we also turn off this horizontal mixing parameterization in the ocean model only in the Lab Sea. So we have like this little mask in the Lab Sea where we turn this off. And so it's the combination of those things that really helps keep the Lab Sea unfrozen. So this old idea of once frozen, it stays frozen is not necessarily the case anymore. So the second thing I won't go into in a lot of detail because David's going to talk after this, but essentially what's happened is in CSM2, we had these melt ponds that were just sort of buckets that sat on top of the ice. And what David's added is a more sort of realistic slope topography on top of the ice that takes into account the drainage of the melt ponds very differently. And I'll let David tell you more about that. So here's our timeline. Dave Lawrence showed this yesterday. I've added some colors to just sort of give you an idea of where we are in the process. So we finished steps 1 and step 2, and we're currently sort of doing steps 3A and B and C. So I'm not sure why they were all step 3, but regardless, we have this pre-industrial sort of run that we're running out several hundred years. And then at the same time, there was this full chemistry historical run, and I'll show some sea ice results from that in a few slides. But that run's been completed through year 2013. And then Kristen and Keith are doing tuning of the biogeochemistry in the ocean model. And so these 3 steps are sort of going on right now. And then once all that's done, then we can sort of move to step 4, which will hopefully be later. The 4th column here is sort of confusing, but it's roughly the number of days that it would take to do that process in real time. And then early on, there were some dates of sort of estimated starts for some of these things. So you can see here that the ocean, land, and BGC spin up is hopefully going to start in mid-August. And then after which we can start our official CMIP runs, which are steps 6 and 7 here. So I just want to give you an idea of what this pre-industrial run looks like. And I think you've heard this, you've seen sort of elements of this already. But what we've been kind of doing, and this term really dates me, but we're sort of daisy chaining these runs together. So that means that, well, we did a first run that was maybe 100 years, and then instead of starting it from scratch again, we just initialize a new run from the end of that run. And we just keep going with this process, and then all together, all these runs chained together are going to give us several hundred years of a pre-industrial state that we can use as a spun-up state for ocean BGC. In the purple curves, you can see these are the full chemistry, pre-industrial, and then the historical run, which is already done. So some sea ice results. So we have this full chemistry 20th century run, and we had done earlier iterations of historical runs as well. So, I know that these case names are not that meaningful to you, but they're just part of that development process that we've had. And so we did one, about 6 months ago, I guess, whenever the 316 case was, and then this 330 is the newer one. So, but I think some things to highlight here, in general, the Northern Hemisphere mean state climatological extent is pretty good. But the problem that we're seeing, maybe a new feature, is that the minimum's in August, and that's not great. In the Southern Hemisphere, the winter extent is very good, but then we're also seeing in the summer months that we're going too low in these runs. But there is still some ongoing tuning of this. This is just showing the maximum extent in March in the Northern Hemisphere and the September extent. You can see we're sort of at the high side in terms of our minimum and maximum extent in the Northern Hemisphere. So with that, I'll just sort of leave up a summary, but this is sort of where we're at. And there'll be ongoing discussions about sensitivity experiments and manuscripts that we want to do with the new sea ice physics. So thanks.
All right, if we have one question, we have time for one question. All right, if you have other questions, ask Dave sometime at a break or at lunch. So our next speaker is David Clemens-Sewell, and as Dave said, he's going to speak to us about the new parameterization for melt ponds. I'll give you at 9 minutes if you go over the 8 on the 1.
Okay, sounds good. All right, good morning, everyone. Thank you all for being here. I appreciate that the organizers put the Davids together and the Josephs together in the... So before I begin, I want to acknowledge the work of the literally hundreds of people required to make this kind of observation and modeling work happen. And so there's my direct co-authors are listed up there, but I'll note that this work relied on the efforts of the Mosaic expedition, the CICE consortium, and the CESM project. And the future work relies on the contrast expedition. So as Dave provided a really nice introduction to, I'm going to talk today about melt ponds. Since this is a 9-minute talk, I'm going to kind of blaze through some melt pond background and physics, and also what the ponds were doing in CESM2, and hence why we decided to go down this path of having a new parameterization. And I'll try to go quickly enough that we have time to talk in a little bit more detail about what we are seeing preliminarily in terms of the sea level ponds in the CSM3 development runs. But first off, just a very brief introduction to what a melt pond is. Melt ponds are puddles. They form on the surface of Arctic sea ice every summer. Spatially, horizontally, they're, some you could step across and others are big enough that a 100-meter long ship could fit inside them. Vertically, most melt ponds are fairly thin. You could walk through them without them going over your rain boots, although for more ridged, thicker ice, there's great examples of much deeper ponds. And although they're not something that we encounter regularly in our daily life, melt ponds are both quite extensive and actually quite important to the Arctic system as a whole. So this is a very, very rough estimate that at the peak of summer, there might be about 2 million square kilometers of melt ponds in the Arctic, which is roughly 40% of all freshwater lakes on Earth combined. And that's simply because the Arctic occupies a vast area. And their impacts, as Earth system modelers, the primary impacts we tend to think about concern light. So melt ponds have much lower albedo, as is being measured by Nora and Savannah in the upper left image there. They also allow a lot more light to transmit into the upper ocean, as is being observed by Avi's remote operated vehicle down there. They have a number of other important impacts on the system as well. And in terms of pond physics, we actually understand very well the basic steps to pond formation. In the springtime, very early summer, snow and ice melt pools and depressions on the surface of the ice. Because of the lower albedo, these depressions preferentially melt downwards, such that the base of the ponds sit below sea level. And this is critical because once the ice becomes fully permeable, any water that's above sea level will rapidly drain off the ice, and it's only by having water below sea level that you can sustain a melt pond. And in a very, very large number of ultra-high resolution satellite observations, we see that melt pond fractions generally stay between about 15 and 35% for sort of mature stage 3 melt ponds. I already mentioned that melt ponds are much darker than the surrounding ice. I'll mention briefly that they have considerable variability in their optical properties as well. This is something we'll look at more in future work, I think. All right, so what were the melt ponds doing in CESM2? Well, unfortunately, melt ponds in CESM2 occupied a considerably greater area fraction than we actually observe in the field. It's shown in the upper left plot here, comparing a couple of field expeditions with the nearest grid cell within CESM2. And simultaneously, they also show much higher albedos in the model, or in CSM2 at least, than what we see in person. And somewhat remarkably, these two biases actually offset almost perfectly. And so compared to sort of present day and observations from the 90s, the grid cell mean albedo for the ice-covered area for CESM2 actually lines up really, really well with the observations. And I will say very briefly, we investigated why the coupled model CSM2 was having this discrepancy, and largely it comes down to the pond physics itself. It's not necessarily an issue with the overall surface energy budget or anything like that. So grid cell mean albedo is okay. Why am I up here, trying to convince you to care about melt ponds? Well, even if we can get the grid cell mean albedo right, right now, we don't have any guarantee that that's going to keep happening, or maybe would have happened in past ice states. It also, if we need a bias in melt ponds to get our surface energy budget right, then that's going to limit our ability to use data assimilation and to improve the sort of physical realism of the system generally. And finally, I'll remind everyone that albedo is not the whole story, particularly for the marine ecosystem, where light transmission into the upper ocean is also very important. So based on what we observed in CESM2, we set ourselves a few goals for this new melt pond parameterization. Specifically, we wanted to improve the physical realism of the pond processes and still agree well with observations and not cause any major issues with the grid cell mean albedo, because that would cause all sorts of biases that then Dave and others would have to tune out of the coupled model. I won't go into the details of the parameterization, but we developed this new parameterization for which, if you want, you can remember the key thing is that the meltwater can sit below sea level, and hence there is a reservoir of meltwater that's protected from drainage. And so we tested this new parameterization initially in a single column model configuration using observed atmospheric and oceanic conditions from the Mosaic expedition. The new parameterization does a really good job of agreeing with observations, as you'd expect, since we developed it from them. And thanks to a lot of work from Dave, Tony, and Elizabeth, we were able to move this parameterization into CEIS, where it is currently available for anyone to use. And somewhat remarkably, when we do these simulations in standalone CEIS, so with a forced atmosphere and ocean, we see almost no difference in the sea ice mass budget. So you see basically nothing on these two plots because of that, because the grid cell mean albedo in a standalone configuration stays similar, and so the ice mass budget doesn't really change very much. Does anyone want to guess what happens when we put it in a fully coupled model? I see some laughters. So we get massive changes when we put it in the fully coupled model. These are, again, I should stress, these are in CESM3 development run, so I can't assure you that this is necessarily what would happen in the final CESM3 model. But when we switch from using the former parameterization, the level pond, which is the left column in these plots, to the sea level ponds, which is the new one, the middle column in these plots, we see that our ice thickness drops by about 1.5 meters. I'm just going to show August values for simplicity. We also see, again, in the coupled model, a big shift in the grid cell mean albedo, a difference of 0.1 to 0.2. And we also see differences in the pond properties. So the top plot here is showing the true pond fraction. So this is the area fraction of meltwater on the ice, irrespective of whether or not it is covered by snow. That last bit will become critical in a second here. And so the level ponds are generally greater pond fractions than the sea level ponds, as we'd expect from the physics. However, when we look at the radiatively effective pond fraction in the bottom plot there, we see that in the level ponds, there's much less radiatively active pond area, especially throughout the Central Arctic. And the reason for this is because with the level parameterization, we are having persistent snow stay on top of the sea ice throughout the summer. That's shown in the top left plot there. And that combined with the way that the level pond parameterization produces very thin ponds means that the little bit of snow that's left around is more than enough to bury the centimeter scale ponds in the level parameterization. And so in the interest of time, I'll skip over that. So thank you all very much for listening. Sea level ponds is available in CEIS 6. If you start using it and run into issues, please let us know. And yeah, I'll leave the next steps up there.
All right. Thank you, David. In the interest of time, I'm going to ask you to ask any questions of David at a break or lunch or to email him. And our next speaker is going to talk to us a bit about some of the machine learning efforts that the Polar Climate Working Group is contributing towards the machine learning enabled CESM3. So this is Dia Zhang, and 9 minutes, oh, 9 minutes. It's been 9 minutes.
Okay, yeah. Okay, can you hear me? Okay. Okay, yeah, first of all, thanks for having me. I'm a PhD student from the University of Bremen in Germany. And I would like to give special thanks to Dave Bailey and Marika, who have been hosting me for the second time. So it's great to be here again. So yeah, I'm going to be talking about how we've been developing a machine learning-based parameterization of CI's flow perimeter for CESM3. So as you can see in this photograph here, the size of flows varies greatly, ranging from centimeters to kilometers. And as Dave already perfectly explained, it is impacted by several physical processes such as thermodynamic melt and growth, flow welding, and flow fracture. And yeah, so the novelty in CESM3, again, is the two-way interaction between sea ice and waves, which is enabled by the so-called flow size distribution, or the FSD, which encompasses all the aforementioned processes. And so the FSD receives sea ice and wave information, and the only FSD variable that is fed back to the sea ice thermodynamics is the flow perimeter. Specifically, flow perimeter is used to compute the sea ice lateral melt, which is described as the product of the lateral melt rate, the total perimeter of flows per unit area, and the sea ice fraction. And what flow perimeter describes can be seen in this schematic here. So you see two model grid cells where the sea ice fraction here is the same, but in the lower panel you see that the sea ice is more fragmented, which is associated with higher perimeter values. So the higher the perimeter, the more fragmented the sea ice is, and therefore more sea ice area laterally is exposed to the warmer open ocean, which then leads to higher lateral melt. The caveat of this of the FSD scheme is that it is computationally expensive, so the FSD increases the size runtime by a factor of about 2.28. So the goals of our study is first to reduce the computational costs associated with the FSD scheme by parameterizing flow perimeter using typical climate variables, so excluding FSD-related variables, and learn more about the governing variables driving flow perimeter. So this is the workflow of our study. First, we generate training data from fully coupled pre-industrial CESM3 runs, where the FSD is enabled. Then we develop a machine learning baseline model, which is a simple multi-layer perceptual neural network that performs point-wise prediction. And then we perform sequential feature selection, which is a machine learning method that gives us a ranking of the most important input features. And we do that because we want to develop parsimonious models, so models that perform well with as few input features as possible, balancing model error and complexity. And in the end, we want to couple our ML model online to CESM using the Fortran PyTorch bridge. Okay, some offline results. So this is the sequential feature selection ranking, which gives the subgrid scale ice fraction as the most important input feature, which makes sense because the model then knows the sea ice state, so where ice is thinner or thicker, followed by significant wave height, which informs the model when wave fracturing potentially happens, followed by sea surface temperature, ocean heat content, and specific humidity. Here you see the ML models trained on, for example, so SFS1 refers to the model trained on the first input feature, SFS2 refers to the model trained on the first two input features, and so on. And the models are evaluated on the year 3 or 4 of the fully coupled pre-industrial run. And you see that especially when including significant wave height, it drastically reduces the error. And here you see the monthly root mean squared error globally for the Arctic region and the Antarctic region. And you see a similar pattern here that including significant wave height really significantly reduces the error. And for the sea surface temperature, you see here in the Arctic summer that it slightly improves the performance. So we decided on using the first 3 input features as the final input set. Okay, so now we also want to know what our machine learning model actually learned. So therefore, we applied an explainable AI method, which is called the accumulated local effects, or ALE, and it gives you essentially like partial dependence plots, excluding physically or unrealistic feature combinations when perturbing the individual features. So here, for example, you see the effect on predicted perimeter on the significant wave height. You see a positive relationship, so meaning increasing significant wave height increases perimeter, flow perimeter, which is associated with more fragmented sea ice. And you see that after a certain significant wave height value, the relationship somehow plateaus. And that makes total sense because you can't make the flows infinitively small. And here on the right panel, basically from right to the left, you see that the thinner the ice, also the higher the perimeter value, which makes sense because thinner ice tends to be more fragmented. Okay, so first online results. For our online experiments, we used we branched from the spin-up run from the alpha 080 case where the FSD is turned on. So from year 49 onwards, we just did 2 years of simulation, again, just for preliminary results. So we conducted 2 additional experiments where we turned the FSD off and then with our ML-based parameterization. And you see that, looking at the runtime here, that our ML parameterization compensates about 91% of the FSD cost. Again, preliminary results. Here you see the monthly mean of flow perimeter for March and September for each hemisphere on the left panel with the FSD turned on and on the right panel with our ML parameterization. So you see that towards the flow, towards the ice edge, the flow perimeter increases, which makes sense, so you have more fragmented sea ice. But what you also see here is that our ML model produces higher perimeter values in the central Arctic. And here I would like to remember you that with the flow perimeter, we target lateral melt, right? And that occurs especially where ocean heat content is available, which is the case in the marginal ice zone and towards the ice edge. And I haven't shown it in in the workflow, but during training we we prioritize high perimeter values where the lateral melt is most significant. So when we look at the time series of the lateral melt summed over each hemisphere, you see that the Q5, which is our ML model, not perfectly, but matches well the lateral melt, which is diagnosed from the FSD run. So the impact of the perimeter bias in the cold Central Arctic on the simulated lateral melt is modest. Okay, now to the summary. This is a quick summary. So subgrid scale, fractional ice cover, significant wave height, and sea surface temperature are the main drivers of flow perimeter. And in online simulation, we show that our machine learning-based parameterization compensates about 91% of the computational costs associated with the FSD. And therefore, we built a skillful ML-based parameterization of flow perimeter and successfully incorporated it in CESM3. Thanks.
All right. Thank you, Diajeng. Again, for time, I'm going to ask you to ask Diajeng questions at the break or on email or some other way. So our next speaker is Leo, and we are going to learn about multi-model insights related to variability in the Arctic as it changes. I'll give you 9 minutes. 1 minute then. Okay, hold on. Present. Do you know how to make it like? Where are we? View. Slideshow. Okay, it automatic. We have a PDF and it's not sharing.
I'll just drag it over.
Oh, okay.
Let's see. Perfect.
There we go.
Oh, look at that. Okay. Okay, thank you. Alrighty, hi everybody. My name is Leo Balser. I am a graduate student at the University of Wisconsin-Madison. I work with Hannah Zanowski, and today we'll be talking about Lens 2 and multimodal insights on the internal variability of the changing Arctic sea surface. So, preaching to the choir a bit here, but we know that the Arctic Ocean is rapidly sloughing off its sea ice content, all in extent, thickness, and in area. And as such, we are projected to become seasonally ice-free sometime within the next few decades. And we know that this is caused by the disproportionate heating of the Arctic atmosphere and ocean compared to the global mean, which first began around 50 years ago. We also know that these trends are complicated by internal variability, which gives name to the natural, unforced fluctuations and variations in the climate system, which arise from the many complex and nonlinear interactions between its many components. This is especially true at the air-sea interface, which at present Arctic sea ice acts to partition. And when we pair this with our Hawkins and Sutton style understanding of imperfect initial conditions, this generates irreducible uncertainty, both in reconstructions and projections of trends in the climate system. And this is of particular note in the Arctic, given that there is ample evidence to suggest that internal variability is actually exacerbating trends that were recently observed in warming. And so given that we are removing that sea ice cover and ostensibly allowing our ocean and atmosphere to communicate with each other more, it stands to reason that this natural variability might also change in response to forcing. So with that, our research questions that we'll talk about today are: how does the internal variability of Arctic sea surface temperature respond to the loss of sea ice? And how is this represented in our current generation of climate models and into the future? To answer those questions, we'll be taking a look at a gathering of CMIP-6 models. These were chosen for both the diversity of their construction and for their offering of at least 10 initially condition-perturbed realizations of the climate from which we can estimate internal variability. We'll also be peeking into the future using all 100 members of the large ensemble future forcing scenario. And then that is our domain of interest. Again, the Arctic Ocean bounded poleward of those major gateways shown in red. Today we'll just be talking about sea surface temperature, though do know that we've also repeated this for sea surface salinity, and it tells a slightly more complicated story than 9 minutes can allow for. And then we'll be connecting that with sea ice concentration as well. And while I am referring to the sea surface, we are taking data from the uppermost 3 layers of the ocean component from each of these models, so around 15 meters of depth. Internal variability shown by the letter sigma, and using methodologies that have been proven for over a decade now. We take the standard deviation across all of those realizations at each time step for each respective model. We'll then be comparing decadal trends via linear least squares regression, and then connecting everything with some pattern correlations via a Pearson statistic. All right, so to motivate the discussion of these results, we'll first start by looking at a pan-Arctic and annual mean basis to get a feel for what's happening. The leftmost plots from this panel here, I feel like we're all pretty familiar with this at this point. Onward of the year 1980, and this is taken from the CESM2 large ensemble. We are warming our Arctic Ocean and reducing our sea ice concentration, and that continues on throughout the rest of the 21st century. And if you were to squint at the shading around that more saturated ensemble mean, you might be able to pick out that member-to-member standard deviation is actually increasing onward of 1980 as well. And we can visually confirm that by plotting that time series of standard deviation. I will note that the annual mean basis does smooth over a reduction of sea ice concentration internal variability, which is observed during the fall and summer months for the simple reason that it's difficult to wiggle your sea ice if you don't have any sea ice at that point. And if we consult with our CMIP6 ensembles as well, we see that for the majority of our models, we're already increasing our internal variability between 1980 and 2015, and that signal is, for the majority point, generated within the last 35 years of that historical time series. Now looking on a seasonal basis, given that the Arctic is dominated by its seasonal cycle, again confirming previous results from many other studies, sea ice loss is most pronounced in the summer and fall months of the year, with either a lack of trend or a sharper trend historically in the winter and spring months as well. And looking at the middle and right panel as well, we see that these trends are fairly evenly distributed between the 2 central basins. And now repeating this for our decadal trend in SST internal variability, those look a lot alike, right? And that lends credence to the idea that these 2 trends are linked. And moreover, the fact that this is agreed upon for all of our CMIP6 models lends credence to the idea that this is a robust response to change in the Arctic climate. To get a sense for where these changes are occurring relative to where we're reducing our sea ice, we'll move on to some spatial analyses as well. This is just a selection of our CMIP6 models, and again, this is historical data, and this is just during the sea ice minimum month of September. I've got 50% sea ice concentration contours plotted as well in magenta and gold at the beginning and end of the period to show where we're reducing that sea ice cover. And we've chosen 50% as works as a general proxy for where we're going from mostly sea ice covered to mostly uncovered and thus exposed to atmospheric interactions. Of course, you're still communicating inward of that contour too. And so we'll call out, there's pretty strong spatial heterogeneity with where we're actually losing our sea ice in our historical CMIP runs. This is, of course, the CESM2 CMIP6 version prior to the biomass burning model bias having been addressed. But if we repeat this again for our trend in internal variability, we see that we are pretty well correlated to where we're losing our sea ice, and these increases are occurring with very close proximity to where we're moving that 50% sea ice concentration contour. And that then implies that changing our sea ice concentration is thus a driver of increasing our natural variability of sea surface temperature. Looking into the future with the large ensemble, we see that this trend and correlation continues throughout the rest of the 21st century. If we peek at the other side of the year during the sea ice maximum month, again, historically now, we see that the majority of our sea ice loss in the Arctic is exterior to the central basins. And this is also where we see our trend in internal variability. And crucially, there's not really any trend in internal variability of sea surface temperature underneath that sea ice too. So again, that's kind of our clamping signal right there. Once again, confirming into the future as well, showing similar results that they are tied. So with that, we can summarize by saying that our results are thus suggesting that our increased SST internal variability is a robust and immediate response to warming and the loss of sea ice in the Arctic. And the fact that this is corroborated across all of our CMIP6 models and into the future suggests that this is a robust physical response. With that, thank you.
All right. Thank you, Leo. We have time for one question, if anyone wants to come up. Go ahead, Laura.
So I'm interested personally in heat waves, surface heat waves in the Arctic, and I'm wondering, typically ocean heat waves are defined by an exceedance of some standard deviation, and it's pretty tricky in the Arctic because there's very little variability in SST, as you've just shown when it's sea ice covered,
right?
And then that variability changes dramatically. Do you have any ideas or opinions on how one might define heat waves in sea surface temperature in the Arctic, and how, and instead of just a simple standard deviation, but how to relate that changing of surface temperature to changes in temperature that include the fact that there's no variability underneath the sea ice?
Yeah, shoot. I mean, that's a great question. I know with the standard deviation, you define like a certain threshold according to your pre-industrial conditions, and then you have your shift and emergence years, right? Right. As far as how to relate that to the lack of variability when you're ice covered, I'd have to think more about that, but that's a really, really interesting question. I think in general, the fact that we're changing our variability does still have implications for, we assume that it's irreducible, but that doesn't mean it's stationary, right?
Yeah.
So,
yeah. Yeah. Thank you.
Thanks.
Awesome. Thank you, Leo. And I did see there were 2 questions online, and we'll try to do a better job of addressing those if they're online. But CC, the sea level ponds is the default for CESM3, and Dia Zhang, could we use the flow perimeter to parameterize wave attenuation? I think maybe could be investigated.
Yeah, not directly, because I think what is used in the wave attenuation is the representative radius, right? So, and that is another descriptor from the flow size distribution. So, not directly, I would say.
Everyone's going over, it's okay. It's hard. All right, so our next speaker, thank you so much, Dia Zhang, for coming up. Our next speaker is Christine Shields to talk to us about predictability in the Antarctic.
Thank you. Thank you for coming to the presentation. I appreciate you being here. As Alice said, I'm going to talk about the importance of teleconnections for Antarctic storms, and I'm going to sort of focus on atmospheric rivers, but everything I say is really going to be applicable to storms in general. And a brief moment to thank the team members there. Science is always done in a team, so I want to make sure everyone is acknowledged. So the spoiler here is I'm just going to cut to the chase and just give you the end, but the main thing I really want to communicate. So we look at modes of variability, things like SAM, Southern Annual Mode, or Pacific South American modes 1 and 2, which are really important ones typically for Antarctica. But these things often step on each other. They're either amplified or damped, or there's lots of other stuff going on. And it's often hard to disentangle them. So I hopefully will convince you at least to start thinking about perhaps using just a simple zonal wave analysis rather than the modes of variability themselves, as a potentially cleaner path to predictability. The zonal wave pattern is sort of the end result of everything sort of stepping on each other. And so I think that might be a better path. So you can think about that as I step through the presentation. I don't really think I need to motivate in this crowd the importance of what storms do to the cryosphere. But this is this figure is from this really nice review paper that was out last year that talks about atmospheric rivers and their impact on the cryosphere. But the big impact, of course, is precipitation. So if it's cold, it's going to accumulate. If they're warm atmospheric rivers, they could potentially contribute to snowmelt. But there are other things, such as these storms and atmospheric rivers often are very windy, in particular for a complex topography like the Antarctic Peninsula. You can have these wind events where you can have this adiabatic warming and then cause melting and such. I'm really just going to focus on the precipitation impact here, just sort of briefly. This is more of sort of a dynamics and a mode of variability type of talk, but that is sort of why we care about looking at these different types of teleconnections, because ultimately they feed back onto the cryosphere. Okay, so just a quick methods slide. I'm using large ensembles. I'm going to compare CESM2 to E3SM2, and I'm going to use MERA for validation. I'm not really looking at trends, I'm looking at two different base states, so like the historical period, and as well as the future period using the SSP3 simulations. Okay, so for the atmospheric river piece, I'm gonna show you briefly some metrics on precipitation in atmospheric rivers. And to do that, we do storm tracking. And so the method I typically use is an Antarctic specific tool. It was developed by Jonathan Willey a number of years ago. It's been applied widely. It uses a 98th percentile threshold to determine what the moisture content is. And when we look at moving into the future, there's always this moving base state problem. Like, what do you use for your threshold? And so, we've done two different ways. We've used just the straight up historical threshold, and we've also used scaling by Clausius-Clapeyron, which will sort of take out that just increase in detection, because it's just moisture everywhere and you're going to hit that threshold faster. This is a dynamical analysis, so I'm really just using the scaling version here, but you can see the comparison there. And I'll note the zonal wave 3-like pattern. You see this is a dynamical signal. This is also just a brief way, so you understand what's going on with the actual ARs, or we're talking about climate change, so this is just the climate change piece of the heat map of where the atmospheric rivers are falling. You just, rather than a wholesale increase, you just sort of see a shift in the pattern, again, a zonal wave 3 pattern. Okay, so that said, now let's move on to the teleconnection piece. I'm gonna show you some information from two sea level pressure-based modes of variability, the SAM and the PSA2. This figure is just showing you the different models and reanalysis. Yes, there are some biases, but generally both of these models do a decent job of actually capturing these modes. So what happens when we look at these two different base states? So here, these are PDF distributions of the variance explained of these EOFs, because we're defining SAM and PSA2 using the EOFs. You can see, if you look at this distribution of the historical period compared to the SSP period, you can see some shifts and things that are happening in these two different climate states. The blue is the historical, the orange is the SSP, and you can see for both models, generally what you're seeing is this a decrease in importance for the SAM in terms of the variance explained, and an increase in the PSA2, which is a zonal wave 3 type pattern. Not saying that the southern annular mode is not going to remain dominant. It remains the dominant, but it's just becoming less dominant. Well, why is this the case? We looked at a lot of different things, and this is just sort of the bottom line. This is a very short talk, so it's gotta just try to do the most important information. So this is looking at the zonal wind, and the top rows are the mean zonal wind, and the bottom rows is the variance of the zonal wind. And these are vertical cross sections in the vertical in the atmosphere, and then by latitude in the x-axis. the top rows are showing you the mean value. So even though the mean value of the zonal wind is increasing in between these two different periods, the variance of the zonal wind decreases. And so this is what explains that decrease in the dominance of SAM, is the decrease in variance of the zonal wind. All right, so I know I talked about, in the spoiler, it was like I wanted to start thinking about this in zonal wave 3 space rather than motor variability space. And so this is just looking at the zonal wave 3. And so there's a couple different phases, and it's just a shift on where the centers of action actually occur. And if you look at it, with both of these different phases, you see the shift and increase in zonal wave 3-like patterns as we move into the future. So again, the oranges are the SSPs. All right, so now finally getting to the atmospheric river, the precipitation and impacts, the cryosphere piece. Here, instead of looking at different modes of variabilities, I'm actually just looking at the zonal wave 3 pattern and how that is interacting with the atmospheric, with the precipitation that you get out of the atmospheric rivers. And so this is sort of a lot to digest in just like a few seconds. But the cheat sheet here is the blue, the anti-correlations there is when you have essentially offshore flow. So they're anti-correlated. And the reds is when you have onshore flow, and so that's when you have the correlation. So where you are in your phase space will correlate to if you have onshore flow or offshore flow, and that very well correlates with this precipitation. And the correlations with the zonal wave 3 patterns are actually more robust and significant if you actually just look at the PSA2, which is where I actually started with all of this. Okay, so key takeaways. There's 2 key takeaways I want you to come away with. One was that, the intriguing result we see with the SAM and the decrease in variance. This is more related to the decrease in the variance in the zonal wave than for example, than an increase in waviness. So it's really just that decrease that's driving that change. And then the other key takeaway is I want to start thinking about using zonal wave 3 instead of these different modes of variability as a way and a cleaner path to predictability. And I'll just leave it at that.
All right. Thank you, Christine. We have time for a question. Anyone? Are there any on? Yeah, go ahead.
Hi, Christine. Interesting talk. I've seen in other analyses looking at like zonal wave patterns separating into the low order numbers and the high order numbers.
Mm-hmm.
Have you thought about, instead of just looking at zone 3, like looking at zonal wave numbers 1 through 3 and then like 4 through 6 as a way to separate those?
I'd love to do that. I didn't have time to show it, but I did look at zonal wave 4, which is super intriguing, and it's a whole other talk. But the bottom line with the zonal wave 4 is that, like a lot of these modes of variability, and even with the zonal wave 3, the West Antarctic area just has greater predictability and greater, correlations. And it's hard to find modes of variabilities and teleconnections that are consistently and robustly important for East Antarctica. But zonal wave 4 actually could potentially be that. You see a really nice correlation with at least atmospheric river statistics in zonal wave 4. But the bad news is that when you start looking into the future, it falls apart. So anyway, that's a very, but I completely agree. It'd be a wonderful thing to start to look at. Yeah.
All right, thanks, Christine. So our next speaker is online. So we have Joey Schnaubelt, who's going to talk to us about atmospheric river detection algorithms and or different atmospheric river tracking methods in the historical and future. And you are sharing your screen. We're seeing the presenter view with your notes. So.
Okay, 1 second. And then, is that good?
Yep, that's good. And at 9 minutes, I'll pop in and just say 1 minute left.
Great. Yeah, sounds good. So thanks, everyone. My name is Joey. I'm a grad student at the University of Connecticut. And today I'm really happy to be presenting the ArtMIP polar synthesis. So this is our effort to kind of compare and contrast different atmospheric river tracking methods in the historical and future climate. And real quick, I want to thank my co-authors on this, Kyle Mattingly, Michelle McLennan, Christine Shields, and a large team from the ArtMIP community. So I'm really happy to be following Christine here. I don't really need to tell you what an atmospheric river is or anything like that, but I'll tell you about ArtMIP. So this is the Atmospheric River Tracking Method Intercomparison Project, and it's kind of a coordinated effort to quantify uncertainties in AR science based on the choice of methodology. So why do we have different atmospheric river detection tools, or ARDTs, as I'll call them? So this is an example plot from a paper a couple of years ago. So it's showing integrated vapor transport. So this is just the vertically integrated atmospheric vapor projected onto the wind component. They're commonly used to track ARs. And these lines outlining this feature are different ARDTs identifying different atmospheric rivers. And so you can see there's a bunch of different geometries there. And there's also kind of some features being detected over here that not every algorithm is picking up. Sort of the reason for this is that different ARDTs kind of use different parameters. So there's different geometries, you can require different shapes, different thresholds, depending on how much atmospheric vapor you want there to be, and also different like time requirements and that sort of thing. But the key point here is that ARDTs are optimized for their specific purpose. And for this study, we're interested in those which are optimized for polar use. And Christine showed this figure, so I don't really need to go into any details. Why do we care about ARs at high latitudes? Kind of the key takeaway is that they bring a bunch of precipitation and potentially heat to ice sheets. They can drive up sea ice melt and wind circulation or wind circulated sea ice breakup and that sort of thing. So just getting into the results. So we've compiled a list of different ARDTs. So these are all different methods for tracking ARs, and all of these have some sort of change for polar detection. And these are all ARDTs that we've used to identify storms in MERA 2. So getting into the results. So at this top panel here, we have a sample time slice for the Arctic and for the Antarctic. This is IVT as shown in that figure previously, and each one of those little outlines is a different algorithm detecting atmospheric rivers. So you can see that there's a ton of variability in the geometry of these storms detected for even the same time slice. There's a bunch of storms kind of in the interior Arctic and et cetera that are only detected in a couple of the algorithms. So tons of variability based on the algorithm that you use. Kind of in the zonal and annual mean, we've also looked at kind of the AR IVT here. So this is just showing us that different algorithms have a lot more moisture in the Arctic and Antarctic than others, so highlighting that depending on which algorithm you choose, you might get quite a variable response in how much moisture there is. And the same is true for area, where different geometries lead to different kind of zonally averaged AR areas. Now, if we're looking at the full fields, what we're interested in is how AR activity changes everywhere. So this plot is showing you the AR frequency. So this is hours per month that an atmospheric river is present at each one of these locations. The top 10 is for the Arctic and the bottom 10 is for the Antarctic. And you can see by virtue of the coloring we used here, there's sort of 3 different categories of AR detection for all the different algorithms that we're cataloging. We have our sort of high frequency and purple storms. So those are kind of these ones up here in the Arctic and in the Antarctic down here. So those capture a lot of storms at high latitudes. We have sort of our average in green. That's kind of our medium frequency ARs on the bottom here and here and here. And then finally, we have our sort of low frequency, which is only really showing up in one algorithm. That said, that algorithm tends to capture some of the most intense storms. So we were hoping to catalog this. If you want to use ARs or AR detection in your own research, you can kind of use this to base your algorithm selection. For an example, if we're interested in storms that penetrate the ice sheet interior, these algorithms don't typically capture a lot of storms over the ice sheet interior, while they do excel at the coastlines. That's a consideration you might want to make in algorithm selection. Now, a big thing that we were interested in this project is how the selection of different atmospheric river detection tools can give you different AR impacts. And so to quantify that using first the MERA 2 data, we've been using kind of statistically downscaled surface mass balance and melt data from RACMO 2, which is forced by ERA 5. So this just gives us sort of high resolution ice sheet impacts that we then associate with our detected ARs. And so here's our 10 different algorithms, and you can see right away that just based on algorithm detection, you get a wide range of possible AR SMB and AR melt. So to kind of quantify that, this is sort of the max and minimum case. We get 10 gigatons of SMB at the minimum, up to 200 gigatons just for Greenland. Now the same is true for Antarctica. We get this huge range in potential SMB and melt, just depending on algorithm, and that range is 24 gigatons up to 800 in kind of the maximum case. So the point is that there's a large impact on our interpreted AR melt or surface mass balance just by choice of algorithm. Now, finally, choosing a different ARDT might give you a different response to future climate change. And so to kind of quantify this, we've looked at the CESM2 large ensemble. So we're going to be comparing SSP 370 scenarios using 3 different members to the present for a subset of algorithms. Here's what those results look like. We've picked 6 algorithms from our larger list that sort of encapsulate the whole range of different AR detection methods. And so on the left, we have the Arctic, and on the right, we have the Antarctic, and this is just showing the AR frequency change as a percent. So some respond really strongly to moisture or storm track. So these more moisture-dependent algorithms get this really large response, whereas others seem to just get that poleward shift of the storm track that we expect for the end of the century. Similarly, some were exclusively storm track driven, and others we see a very small change. So these ones tend to be the more statistical based algorithms that just, maybe they look at the high percentiles of IVT change where they don't necessarily look at something like a change in moisture. And these can have a pretty big impact on our results. And then finally, what's the change in future AR impacts depending on ARDTs? So to sort of kind of talk about this, we've looked at the AR precipitation at the top. So this is the precipitation from CESM2 data associated with atmospheric rivers, the anomaly of the SSP 370 scenario compared to historical. And you can see that generally it gets a bit wetter. On the bottom here, we've looked at AR melt. So this is looking at we are using kind of a positive degree day scheme to estimate the melt that might be related to an atmospheric river in all these different algorithms, and that varies quite a bit as well. And of course, the same is true for Antarctica. So circling back to that question, do ARDTs agree on future AR impacts? And the answer that we've come up with is kind of. All ARDTs definitely capture a net increase in precipitation and a net increase in melt over both ice sheets, but the exact pattern and magnitude is widely variable, depends on AR geometry and frequency. All right. And so here's kind of our key takeaways. We assembled 11 ARDTs for polar comparison. We're kind of trying to assess the difference between these two and sort of emphasize their strengths and weaknesses in different cases. The choice of ARDT strongly influences our AR impacts. In this case, we've highlighted sea level rise as being a potential impact. There's also a large amount of disagreement between polar ARs, especially compared to the mid-latitudes that hopefully we're working to discuss, and stay tuned for the paper. And then real quick, I want to thank the Polar ArtMIP team. So these projects are always a big undertaking. There's a lot of people involved, and there's a lot of results that I didn't show in this presentation that will feature a little bit more in the paper. And yeah, that's all. I'm happy to take any questions. And you can also ask Christine any questions if you're there in person.
All right. Thank you, Joey. Do we have one quick question? Are there any online? Nope. Okay, all right. Well, then we will move on to the next one. Thank you so much, Joey. I had not intentionally organized the session this way, though David pointed out that the Davids and the Joeys are grouped together. So our next speaker is Joey Rotondo, and he's going to be talking to us about the surface darkening of surviving Arctic ice. And yep, it looks like you're already sharing. So if you go to 9 minutes, I will try to pop in and let you know that you have 1 minute left total.
Sounds good. Can everyone hear me?
Yes.
Yes. Okay, perfect. So yeah, I'm also Joey, funny enough. I work with CC Pitts at the University of Washington, and I'd like to thank all of my collaborators here. And I'm going to talk about kind of mechanisms for radiative processes in the Arctic and how they're represented across CMIP6 models. So first, some motivation. I'm actually more into the data assimilation side of things. And so my first paper found that assimilating sea ice albedo can improve state estimation of sea ice within CEIS. And so the story going into this PowerPoint is then, can we validate our satellite data to use this operationally? Because that was done in an OSSI framework, or looking at synthetic observations. And so if you look here, you see that we're correlating sea ice concentration and albedo products, and these two lines are the contours between the marginal ice zone, and the Pearson correlation is close to 1. And so this is saying that basically you get a better ice state because albedo is used as a proxy for concentration. But if you note, like, if you look in the central part of the Arctic in May, there's very low correlation there. And so that asks the question, does darkening precede physical ice loss? And as we all know, that should be a yes, but how are models doing at representing that is kind of what we're going to investigate here. And so just to show you that over stable sea ice concentration, so regions where, according to satellite error, we haven't lost any concentration, we still are seeing a decrease in albedo. And so it's significant throughout May through September in the Arctic. And so there's these negative trends that are statistically robust, suggesting that we are losing Arctic albedo where we still haven't lost ice concentration. And partially, you can think of this as the response to ice thinning, but also things like snow loss or potential changes from melt ponds, such as, thinner ice under melt ponds. And so that kind of leads to a radiative question of what is happening in the Arctic. And so I'm going to introduce a sea ice albedo feedback following Aaron Donahoe's 2020 paper. And so I'm going to go into each of these terms in a second to try to help you guys better understand what I'm talking about. But basically, it's the multiplication of an ice sensitivity times a radiative sensitivity. And you can think of it as the additional solar energy absorbed at the top of the atmosphere per degree of global warming. And this is driven strictly by the loss of sea ice. And it allows you to isolate the ice-driven signal from other things like clouds. And so what is the ice sensitivity? Well, it's the change in albedo per degree of global warming. And how we represented this is we did an ordinary least squares regression of the monthly albedo time series against global annual mean temperature anomaly. So we're all in observational space so far. And this makes it robust to nonlinear warming. A lot of people have looked at the sea ice albedo feedback, but generally they've taken like a later period minus an earlier period, and we found that that ended up being very dependent on when you chose your periods to start and end. And we also here assume that all recent albedo changes are due directly to the temperature anomaly, but this captures both the force response and internal climate variability. So take what I'm saying a little bit with a grain of salt when you're comparing the observations to the model. And then so what is this radiative sensitivity term that we're multiplying by? Well, it's the change in the top of the atmosphere net shortwave flux per change in surface albedo. And to get this, we did two observational approaches where we did a one-layer single isotropic model where you have just one atmospheric cloud layer. You assume all absorptivity occurs above the cloud layer, and then reflection occurs kind of converging iteratively below that cloud layer. And it gives this nice, simple expression for radiative sensitivity in an isotropic approach. And then you can use the series EBAF data to actually calculate through 3 equations and 3 unknowns what that value is. But we also took ERA 5 atmospheric kernels using the RRTMG, which we've used for things like CESM to understand kind of how changing the surface albedo impacts the top of the atmospheric flux. And so if you compare those two approaches, on the left here we have that isotropic approach, and here in the center we have the ERA 5 kernel. And you can see spatially they agree very well in what the radiative sensitivity is, so the change in the top of the atmosphere to surface albedo. And so if you look at this plot of the difference, white indicates almost no difference, and so the two approaches actually agree very well, which hopefully will give more confidence in the results that I'm about to show. And so Aaron had started this work fundamentally in 2020, but he had not considered the impacts of, he just looked at the loss of ice, so where you lost ice concentration, but he didn't look over the central Arctic where ice is simultaneously darkening. And so I've split these two terms into the extent component, so anywhere that there was a significant loss of ice, and then the darkening component where we didn't see a significant loss of ice over the satellite era. And this will capture contributions from things like snow loss, ice thinning, and melt ponds as well. And then to scale it to global climate metric, you multiply it by the area of the Arctic Ocean and the number of melt months in the year, which we assume to be 6. So no sunlight in the winter, essentially. And so here are some of those results. So what I'm showing you here on the left is the observational period that matches our historical run, so through 2014 and starting when we had observations, or 1982. And then if we add the last 10 years. And so you'll see that this orange component is non-negligible, and this represents the area where we haven't seen any significant loss of ice. And so we are losing albedo over areas where we haven't lost ice yet. You'll see also if we add the last 10 years, there's this decline in the sea ice albedo feedback. So it appears that potentially internal variability or a change in ice state might be playing a role. Those are questions you can ask me later offline. But really importantly, there's strong agreement between this left side and this right side, and those were the 2 different radius sensitivity approaches I showed. So basically, we have good trust in our observations that this is the value we observed over this time period. And so if you look spatially at this pattern, the extent or loss of ice area in this top row is mainly over areas like the Barents Sea and Beaufort-Chukchi Sea. And again, this left column is using Ceres and this right is using Era 5. The darkening term is more spatially heterogeneous, but located over much of the central Arctic. So it suggests that, regional trends and things like snow loss or melt ponds and ice thinning may be playing a role. And then largest uncertainty in this right plot is occurring in the marginal ice zone. And so we're at least certain, or we're more certain that there is loss of albedo over central Arctic areas. And so now getting to the results that we're interested in, here in the middle is the CSM2 model. We can see that the observational sea ice albedo feedback, which is this red shaded bar plot here, it sits above the 2 sigma above the multi-model mean, which is this dashed line here. And so our lower bound of our observations are above what the CMIP6 model is producing for the sea ice albedo feedback. All of these models are doing a pretty okay job of capturing, the difference between loss of ice and areas that the ice is darkening, but overall the trend is suggesting that we don't have the right magnitude for the sea ice albedo feedback. And so that's something I'm happy to talk about later. Just to give you guys more confidence in our observational results, we compared our observations to a bunch of different field observations. And so this is the satellite product Clara A3 we're using, and we matched it to Mosaic and some NASA products, and you can see there's very good agreement between those 2, which is amazing given the spatial scale of the satellite and what we observe at the surface. There is a slight negative bias, but we don't anticipate that impacting too much our climate trend that we've calculated. And so I'm going to leave my takeaways up in the interest of time so people can ask questions, and thank you for listening.
Thank you, Joey. Do we have a question in the room or online?
Hi, Joey. Really nice talk. I'd love to talk more offline. But really quickly, you talked about the impact of uncertainties in satellite albedo products. I wonder about the impact of uncertainties in satellite ice concentration on your analysis.
That's a great question. So in terms of the actual product and how we derive the sea ice albedo feedback, we are looking at areas where there were more than 15% sea ice concentration. So that could also play a role in kind of the marginal ice zone. But I'm not sure I have it here. We did some backup. Well, basically, we did some backup analysis that looks at kind of the collocation of where the ice edge is predicted between the concentration and the albedo product, and it does pretty good at representing where that ice edge is.
Awesome, thank you. All right, we're gonna move on to our next speaker, who is Ed Blanchard-Wigglesworth, who is the other Polar Climate Working Group co-chair. In case you haven't met him, you should come up and say hi. I think this might be your first time visiting since you became co-chair. And then to make it full screen, here, hang on, maybe I can make it work. All right. 9 minutes.
Okay, thanks, Alice. Hi, everyone. I'm Ed, and I'm going to talk about something maybe quite different to very different topic of like actually, we know the Arctic is losing sea ice, climate change is going to continue, and so more than a few people have thought about, well, could we actively counteract that? So I'm going to show results from fairly recent fieldwork experiments that aim to thicken Arctic sea ice, and how we combine in modeling studies to understand, to better understand how, the response of these experiments. And I'm going to use this image here to remind you that sea ice is covered by snow most of the year, and the snow acts as an insulator, so actually the snow on top of that sea ice slows down sea ice growth. And there's been this idea around for a few years that maybe you could thicken Arctic sea ice by flooding it in the winter, and this is the schematic kind of on the bottom there, that if you were to flood the surface of the sea ice and the snow, you would saturate that snow with water, and you turn it into basically sea ice or snow sea ice. So you basically have that new ice layer, but importantly, you've reduced the amount of snow on top, and having less snow should accelerate sea ice growth, and you should have an accelerated basal ice growth. So there's been a few modeling studies that have basically run model experiments to see what the impact of this would be. And in general, they found that you would thicken Arctic sea ice. The impact on both Arctic climate and global climate from that thickened Arctic sea ice isn't quite clear. But what I want to start with is fieldwork experiments that have actually tested, well, would you even thicken the sea ice in the first place? So I've been collaborating with a UK non-profit company called Real Ice, and they've, over the last couple of years, they've done small-scale fieldwork experiments, and the main one has been in Cambridge Bay in Canada over the last couple of winters, and I'm going to show you a few pictures of how we do this. It's quite simple. You go out to the sea ice. This is fast ice in the bay, and you drill a hole. You put a pump in the hole, a pump that's attached to essentially a hose. You put that into the hole. The ice here is maybe a couple feet thick, and basically you switch that. You plug it to a battery, and you essentially flood the surface of the sea ice. And these batteries lasted for about 4 hours, and after a few hours, you essentially made a big puddle. You saturated all that snow on top of the sea ice. This is our very own Molly Waringa in this picture. And you can see that here it stopped pumping because the battery ran out of juice. But you can see that after a few hours, we would basically take that out, and then we'd walk over to the next area and do the same thing. Okay. So what happened? Here on the left, I show you the observations of ice thickness throughout the winter and spring season. So this is 24-25, and in black, I'm showing the control areas. So this is where we didn't do anything, and you can see the ice thickened from about 50 centimeters in December to about 1.5 meters or 160 centimeters by the end of the ice growth season in May. And then the different colors are the different treated areas where we flooded, and we either flooded once in the season, and that was in the red and magenta, so either in December or January. And then a few other areas we flooded twice, both kind of early season and later in February. And you can see that in all those regions, we ended up with thicker ice. The take-home message here, shown on the right by these histograms, is that the areas that we flooded twice, you thicken more than if you just flood once, and we ended up with up to 30 centimeters thicker ice by spring. This is the equivalent figure, but for snow depths. Snow is a lot more variable than ice thickness because of wind distribution and sastrugi. But in general, what we found is that, as we expected kind of from theory and modeling, that the final snow depth in the spring was a little bit thinner than in the control areas. So the control areas, we ended up with 26 centimeters by early May, by the end of the sort of winter. And the flooded areas had 5 to 13 centimeters thinner snow depths on average. This was another result that was unexpected. When we went into the melt season, so the temperature first went above 0 on May 22nd, and very quickly that snow on top of the sea ice melted. And here I'm showing a drone mosaic, like digital imagery of the field site, and you can see by the May 29th, the control area is looking very bluish. That's because it was just covered in meltwater. And those sort of patches in the middle that look brighter, those were the treated areas. And this was also very clear from satellite imagery. This is from ESA, the Sentinel. And you can see the sort of white dots within the red circle, sorry, within the red cross, that's the red square, that's where we, that's the treated areas. And we saw that enhanced brightness lasted pretty much the whole of the melt season. And this had an impact on the melt rates. So we were able to estimate melt rates in the early part of the melt season. On the left, I'm showing estimated ice thickness profiles. In black are the control ones. So end May with just over 1.5 meters, and by mid-June, we were down to about half that thickness. And then the magenta and blue are two of the treated areas. And we can calculate the melt rates, and the melt rates were, 20 to 30% slower over these treated areas, we believe, because they had a higher albedo. Okay, and then I want to move on to work that Molly's led. So she's been using IcePack, which is the size thermodynamic column model, and this is quite appropriate, we think, for a place with fast ice, where there's no dynamics. And she essentially replicated flooding in the model, and that is shown with the bold colored lines. The dots are the observational data, and then the blue lines is what happened in the control run where you don't do any flooding. I've sort of marked where the flooding is by these are the dashed lines in each, these are three examples. So couple places where we just flooded once, here we flood twice, and you can see that the model actually does a really good job at simulating that enhanced thickness. I do want to point out that if you look at how the model simulates the melt season, and essentially one of the main objectives of doing this is that you would have a longer ice season in the summer by thickening the ice. It would persist longer, and we see that in the model. It's a fairly short enhanced ice season length, but part of the reason for that is that the melt rates in IcePack are pretty much the same in both the control and the experiment areas, because the model doesn't know that those treated areas actually ended up having a brighter albedo. So part of the work that we're doing now is to say, okay, well, how could we incorporate those physics into the model to simulate that part of the process? Okay, so there's a summary, and I think I'm probably out of time, so I'll just leave it there. We just published the results from the fieldwork experiment, so there's the reference if you want to know more, and if you want to have questions, just come find me. Thanks.
Thank you, Ed. We do have time for a question, if anyone wants to. Oh, Christine. He was just closer. You both got up at the same time.
So this might be an obvious question, but how do you increase the scale on that? So, you did it in these little control areas. Are there any plans to do something more widespread?
So as you might guess, doing this work with humans is both really hard, and you can only do it in small scales. Realize has actually developed an underwater drone, an autonomous underwater drone that does this automatically, and they've already tested it in Finland, in the Gulf of Bothnia, this past winter. And the goal is to go back to Cambridge Bay next winter and use this underwater drone to do this. I'm kind of shocked at how quickly this is developing. I first came across this idea of this group 3 years ago, and it all sounded like science fiction. And I'm kind of shocked at how quickly things are developing in this space.
Awesome. Well, thank you, Ed. Our next speaker is online. So June, I think you can go ahead and share your screen, and we're going to have a little shift here to talk about Southern Ocean and more marine ecosystem based focus. And at 9 minutes, I'll give you a heads up.
Okay. Can everyone hear me?
Yes.
Okay. So hi everyone, my name is June. I'm a PhD at the University of California, Irvine. So today I'm going to talk about the trade-offs between climate benefits and ecological cost from ocean aerosolization. And this paper has been recently accepted in Nature. So not sure whether. So I'm not sure whether everyone here knows what is iron phosphation. So basically, it's a way to add iron in some seawater, and they will enhance phytoplankton growth and then enhance the biological carbon uptake. So eventually, it will help us to lower the CO2 level in the atmosphere. As a result, ocean iron phosphation has been proposed as a potential MCDR approach. However, like any large-scale disturbance, iron phosphation will have an impact on the marine ecosystem. So minimizing the ecological cost must be considered and prioritized for any types of marine CDR approaches. So there are several potential impacts, such as neutron rubbing, denitrification, and oxygen minimal zone expansion, and reducing biodiversity, and also have disturbance on the fish habitat. And there are already several past studies on modeling the impact on HNLC regions, but past efforts focus on fluorization on HNLC regions because they are motivated by carbon efficiency only. So we here argue that maybe the underexplored subtropical regions might also have some fertilization potential because the ecological cost might be lower. And the reason is that if we add iron in the water where it can enhance infixation, and then the more nitrogen will provide it to the community and will enhance the carbon uptake. So it might also mitigate the neutron rubbing effect. So as you can see, there are a lot of this complicated biogeochemical and ecological process that couple together, and it requires a lot for a model to be able to capture all these feedbacks. So here enters the next generation ecosystem model, which is called CSM2 AP4Z. So this model, the specialty of this model is joint representation of biodiversity and biogeochemistry. And this model is highly process rich. It has expanded community composition, which includes 8 types of phytoplankton and 4 types of zooplankton. And it can be able to capture the following impacts on science-related export efficiency, the dynamic phytoplankton resource demands with fully variable C2 N2 P2 iron, and also it includes explicit representation of infixation, denitrification, and calcification. And finally, the dynamic in the food web in the model can offer insights for impact on fisheries. And this detailed description of this model has been published on James last year. So please check on the paper if you're interested. Before we conduct large-scale CDR simulations, we first validate whether the model can capture the response from the previous in situ fertilization experiments. So this figure shows 1 month of grid-scale fertilization and conduct in the region that's close to the field studies. And the gray bar represent a response from the experiment, and the green bars are the model results. So as you can see, the model can broadly capture the responses both for biochemical sites like chlorophyll, NPP, and carbon export, as well as the ecological shift. So we believe that the model can be able to be used to do further longer scale iron fertilization. So here I conduct 10 by 10 degree fertilization for 60 years in 10 locations. And it includes 4 HNLC regions and 6 oligotrophic sites. And after 60 years of fertilization, I found 3 top efficiency places. HNLC Equatorial Pacific, Southern Ocean, Subtropical Southwest Pacific, and a mild global fertilization. And we also find that the fertilization efficiency sharply declines with increase of fertilization intensity. That means ocean iron fertilization will gonna be increasingly inefficient when you add more iron at one location. We also found that the impact of iron fertilization are inherently non-local. So as you can see in this figure, so the rectangular represent fertilization at the HNLC Equatorial Pacific, and the x-axis represent the local NPP net change, and the y-axis represent the global NPP net change. So you can see while add iron in the Equatorial Pacific will enhance the local NPP, but as the global net change, it is actually a net decline. You can see it more clearly as the global map on the right, like figure J here. So that's the fertilization at HLC region, the Equatorial Pacific. So when we add iron in that location, it will enhance the NPP along the equator, but it will trigger the nutrient rubbing and will largely depress the NPP in adjacent subtropical gyre. However, when we add iron to the Southern Ocean, it enhances the NPP both locally and also non-local downstream along the currents. So you can see there is large scale non-local downstream effect, and it fundamentally challenged carbon crediting. So we found that we here report practical conundrum. We found that the easy to observe indicators are poor proxies for credible CO2 removal, whereas the decisive matrix requires technically difficult global scale observations. As you can see in the figure A here, we found that the only matrix that correlate with final CO2 drawdown is the global carbon export net change. It is not surprising, but it is technically very difficult to measure. But other easy to measure metrics such as export in patch or NPP, both locally and globally, we can infer that from satellite. They don't have a high relationship with the final CO2 drawdown in the atmosphere. So we here report this practical conundrum, and we found that it will be nearly impossible to separate the multiple ongoing fertilizing efforts to accurately assign the carbon credit to each groups. Besides carbon part, we also quantify the ecological cost. So we found that when we put the fertilization box closer to the Central Pacific, it will cause the ecosystem structure to shift to a smaller size. However, when you shift that location away from the Central Pacific, like higher latitude, such as the Southern Ocean, it will push the ecosystem structure to a larger size. Such impact of size shifting will propagate to higher trophic levels because it translates to the net change of macrozooplankton biomass, which are the important food source for fish. And we also found that when you put the box closer to the Central Pacific, it will which has a main oxygen minimum zone, it will trigger faster denitrification and a bigger OMZ expansion. But if you put that box at a higher latitude, such as Southern Ocean, we didn't detect any significant OMZ expansion. So we integrate these three ecosystem vector as one ecosystem risk score. That is biodiversity risk, macrozooplankton loss, and OMZ expansion as one risk score, as showing as y-axis here. And we compare with the fertilization efficiency as the axis here, and we can finally answer the question of what are the trade-off between climate benefit and ecological cost. So we report three tiers of such trade-offs. First is when you fertilize the Equatorial Pacific and also global fertilization, it will give us higher climate benefit and also higher ecological risk. On the contrary,
1 minute.
Oh, on the contrary, when we fertilize Southern Ocean, it will give us higher benefit, but also lower risk. And other box just cluster in the middle, which is a lower benefit and medium risk. So some takeaway is continuous fertilization give us only less than 1 gigaton CO2 per year with a global footprint of impact. And there are three tiers of the trade-off: Southern Ocean, high efficiency and low risk; Equatorial Pacific and global fertilization, high efficiency, high risk; and the subtropical ocean lower efficiency and medium risk. And the key finding is that carbon crediting will be highly challenged by the long local impacts and the weak correlation to easy to measure indicators. Thank you.
Thank you. We can take one question if anyone has one. I will ask one then, which is similar to Ed's talk before. It seems like, okay, maybe the Southern Ocean is one of the lower risk regions with high efficiency, but it would be very hard to get there and be doing all this fertilization. So is there any understanding about like what the cost would be in those different areas and how that plays into the trade-offs as well?
Yeah, I think that's a really good question. I think that is definitely my next step to work on. I think if it determines like which country wanted to do that fertilization. Like if US or China wanted to do that, then you have to ship out all the iron from like northern hemisphere all the way down to the southern hemisphere, and it might be more costly. Then also when you do that, all the transportation and fertilize the ocean, you're also going to emit CO2 doing these processes, and how will that also impact the estimate of the CO2 drawdown? So I think that will be an interesting question to investigate further.
Great, thank you so much. All right, so the last part of this session was a discussion, and I am very well aware that I am between you and lunch, and there's much less time for this. So I'm just gonna very briefly bring up some of the conversations that people within the Polar Climate Working Group have been having and some questions, and then maybe instead of having as much of an interactive discussion in here, I would invite people to go find a table. I'll go try to get a table outside, and we could talk about this over lunch. And if you're like, I do not want to talk about this, then you don't have to come sit with us, but you can also email me or Ed or presumably Gunter, because this applies to both the land ice and the sea ice. So there are a couple upcoming major field initiatives in polar regions. So on the left here, you have Antarctica in Sync, which is obviously Antarctic focused, and it's this global effort to synchronize research in Antarctica and the Southern Ocean. And there are a bunch of different foci, which includes sea ice and land ice and biogeochemistry and things like that. A lot of countries are at least semi-coordinating their fieldwork. The degree to which that's being done kind of varies. I've attended some of the discussion meetings about this. It's not super clear to me that there is a lot of organization of modeling activities. It's very much field focused as far as I can tell, though there is a modeling kind of liaison person to contact. And then one thing that has also come up is that the US doesn't have a national committee right now, nor is there a specific funding stream. Like NSF has not said, oh, we'll put aside X million dollars for this. And it seems pretty clear to us based on the recent kind of town hall that the Office of Polar Programs had, that climate-focused activities are not a priority right now. There are other things I think people could do that would benefit this effort, maybe forecasting and stuff like that, but just to be clear, that was one of the things that was pretty clear in that town hall. So the time frame for this is relatively short. The preparation is going on now, and it's supposed to be implemented, like ships are in the ocean and people are out there taking observations starting next year. And that would be a year or two, depending on exactly when all the activities are happening. But the idea is that it would be before the International Polar Year. All the activities would be done and some of the results could be reported on by the International Polar Year. And that takes me to the other activity, which is the International Polar Year, which is in 2032 to 2033. This is both hemispheres. And it's basically aiming to address global challenges by advancing polar research in both of these regions. There are a lot of sponsoring organizations and countries. Many of them also have national committees. As far as I'm aware, there is no US committee yet. There was a National Academies workshop in 2025. Marika is going to be speaking to a CLIVAR panel in August about polar model observation related research that may feed into something like this. And again, it's less clear if there will be any funds set aside for IPY activities. I think one thing to point out is that it would be possible to approach private donors or foundations about either field or potentially modeling research for these, especially since they're big global efforts, and that could be, higher profile for if they're interested in that. The time frame is a little longer for this, so we're kind of in the planning phase and ramp up from now until 2032, and then the focused year of observations and activities is in 2032 to 2033. And again, modeling, I think, could be involved in these both before the activities to help identify, like thinking about the iceberg rafted debris. Like maybe there are modeling studies that can help us decide where you want to go drill a core to get more ice rafted debris, something like that. Or, sea ice model efforts that would be really useful for planning. And of course, modeling efforts that would be beneficial after all this data is collected to help improve models or test data assimilation or something. So these are the two activities. Just wanted to make sure we're all on the same page about these. So the questions that I kind of put together for the Polar Climate Working Group and the Land Ice Working Group are basically testing or asking people within our community, should the Polar Climate Working Group or the Land Ice Working Group be involved and helping organize modeling specific activities for these kind of field-focused efforts. And if you think yes, I think some of the questions are, should we focus on one or both efforts? Is it, the time horizon for Antarctica and Sync is relatively short. Should we just focus on IPY? Do people have interest in both? And then how would we want to get involved? So these are just some examples. Like if someone is interested, they could serve on the US Antarctica in Sync or the IPY committee as one of the kind of the modeling spokespeople. We can provide a wish list of data, including what format we would like it to be in. I know this was, I think, a challenge from Mosaic despite coordination, but that way, if we want to do model development and we have data hopefully in the right format, that would make things easier. The Polar Climate Working Group or Land Ice Working Group could try to coordinate interested scientists or potentially organize planning workshops, maybe more for IPY related stuff. Would MIPS be appropriate if people are interested in that? And then the who is, if there are people in here who are like, I am super interested in this, I would be interested in serving on a committee or being involved in helping, coordinate activities. We would like to know that. And then some people maybe just want to be informed by like working group email lists, and I could, we can send out email lists to the Polar and the Land Ice Working Group meetings about things that are going on. So those are kind of the things that I wanted to have just to spark discussion. As I said, I think we're officially at lunchtime, and I want to eat lunch and not stay in here talking. So if you're interested in having a conversation about this, try to meet outside, and we'll try to get a table where we can have some discussion, and you can always email me about it as well. And regardless, if things come up, we'll try to, that are relevant to many people, we'll email, the different working group emails. But yeah, feel free to be in touch with us. And otherwise, thank you to all the speakers, and thank you for this polar focused sea ice, land ice, all those sessions.
Okay, well, we'll get started in a few seconds, so take your seats. All right, well, yeah, welcome everyone to this session on storytelling. So, crafting science tools for communities. So, I want to thank you all for being brave and showing up to this rather new format session and not going to the other session. We're going to learn together how to do storytelling. So what's the motivation, what's the outcomes, and what are the different formats for doing this storytelling? So in my plenary talk yesterday, I contrasted two modes of storytelling, or two paradigms. One was the Western scientist paradigm of applying a t-test, quantifying statistical significance, and the other one was a risk manager telling stories about objectives. And if we want to create usable science, then we need to blend these two paradigms, these two ways of telling stories. So I think it's a skill. It's probably not something that comes natural to people. So this session is also an outgrowth of an EOS article that was authored by Mari Tai here and some of the rest of us as co-authors. So the title of that EOS article was Environmental Metrics That Matter. So I mentioned the t-test just now, and we talk about significance, but what about meaning? So there's probably room here to complement a t-test with a narrative of our science that is meaningful to the people who might benefit in numerous ways of knowing about it. So they might benefit from changing perceptions, from taking action, or even from wanting to collaborate with us on a deep level. Okay, well, I think I'll get started by outlining the structure of this afternoon. So before the break, we're going to hear from several speakers who have experienced storytelling. And when you're listening to these talks, I want you to listen for the formats they use in their storytelling, the motivation, the reason they're doing it in the first place, and then also the benefits that they see from engaging in storytelling. And that'll take us up to the break. And then after the break, we're going to reconvene in this room, and we have a 15-minute discussion just sharing how we experienced those presentations. So we're going to discuss, say, commonalities of formats of storytelling and then differences and the pros and cons of different methods. And then we're all going to get up and be active, and it's your chance to develop your own narrative of your science. So a narrative in a way that complements maybe how you typically talk about your science, but in a way that is engaging and opens up conduits to, like I say, broader engagement, perhaps collaboration, and stronger connections with people we don't normally talk with. Okay, so with that, I think we'll get started with the presentations. Before I introduce the first speaker, I just wanted to give a shout out to Alice DeVivia, who submitted a poster to this session. You might have seen it last night that was upstairs. So if you hadn't seen that, please take a look at the break. Okay, so I'm very pleased to welcome Haiyan Tang from North Carolina State University and North Carolina Institute for Climate Studies. So Haiyan is going to present on her experience translating climate projections to actionable risk, gaps in the role of intermediaries. So thank you, Haiyan.
Oh, thank you for having me here. And today I'm going to share a bit of my new learning journey in Asheville, where my institute co-locates with NCEI, and we support NOAA's climate assessment, monitoring, and climate services through this cooperative agreement. So when I was hired in Asheville, I was told that I was the first climate scientist with some modeling background, which can make this transition both exciting and challenging. And in my first year in Asheville, it was like experience of loss in translation. But fortunately, I'm grateful for this WCRP EPESC Lighthouse activity, which encouraged me to lead a series of discussion on this topic, and in the working group 3. And the working group 3 co-lead, James Risby from CSIRO, he leads the climate services at CSIRO. We're co-leading a community perspective paper, which will be submitted pretty soon. So, do we still have the echoes? Well, I arrived in Asheville about a year. About a year after NCA5, the U.S. National Climate fifth U.S. National Climate Assessment was completed. By the way, the director of NCA5, Alison Creeman, please raise your hand. She is in the audience, and she's going to share her stories about NOAA's climate service, the IPG project, shortly. So on the right hand, I'm showing the workflow of NCA5, which has not been discussed a lot in this community. And it generally follows the workflow of the conventional probabilistic approach, which is illustrated on the left hand. In the middle yellow box, it shows how the climate model, climate projection outputs are translated into risk information. It has 2 layers. The top layer is about bias correction, downscaling, ensemble treatment, risk matrix calculation. These are usually done by analysts. Then in the second layer is about information dissemination by practitioners. There's no doubt these climate assessments are critical, but are they sufficient to inform future risk? To this audience, I must be preaching the choir to tell you that many high-impact events are under-resolved by our models, and the probabilistic approach is weak for tail risk decisions. As we translate global scale projections into regional and local scales, the uncertainty increases. So during the discussion with the WCRP, EPSC lighthouse activities, we identified, hey, there are many gaps in this intermediary space. Here, we're highlighting a few of them, such as hazard presentation, translation and integration, data access, usability, governance, coordination, evaluation. But due to the time limit, I'm not going to go to the details. I'd rather highlight just one point, that in the top-down probabilistic approach, these one-way arrows, we need to make them both ways. Co-production is a key for this translation process. We also started to become more aware that the conventional one-way probabilistic approach should be complemented by storyline approach, which is like a physically plausible narrative of climate risk events that integrate hazard, exposure, vulnerability, impact to support decision-making. Unlike the top-down approach, here we start from decisions, not the model outputs, and we want to emphasize that climate risk is context-dependent. Co-production is important. We need to use multiple lines of evidence. And this kind of approach has been advocated by the WCRP, My Climate Risk Lighthouse activity. Under this effort, they have built lots of global hubs. So again, we believe the traditional top-down approach can provide the backbones for climate risk assessment, but this needs to be complemented by the bottom-up risk storyline approach. Under this bottom-up framework, the climate projections can still provide an important line of evidence, but it will not be the only narrative, the full narrative. So we believe co-production is important to risk storylines, and state climatologists can play an essential role in providing local context and information of stakeholder needs. Just imagine if we study weather and we don't know how weather forecast is produced through National Weather Service. This is like, hey, we study climate and we really need to work together with state climatologists and understand how climate services are provided to the community. So NCEI has a long history of supporting state climatologists through the regional climate centers, and my institute has supported the state climate summaries to strengthen the state climate services. So next week, I'm going to go to the annual meeting of the state climatologists. And before that, I really want to bring forward the spirit of this CESM community-driven effort to engage with my new colleagues. What do the storylines look like? Indeed, there are plenty of high-impact research papers on extreme event storylines, but those are not what we have in mind. Here, we want to prioritize real-world impact over impact factors, and we also don't want to just produce some fast attribution communication product. The storylines we have in mind is a decision support, concise document for decision support. It could be just 4, 5, or 6 pages. Taking the Hurricane Helene as example, we want to produce this kind of support, this product that about a year after the event occurred, it should have covers the event description, prediction, projection, impact, and response. So we think this could be a good place for us to reflect, to synthesize the research and operation experience, and to share lessons. To this community, we will really welcome your contribution to the section 3, prediction and projection, to really understand, hey, what are where the models do well and where the models struggle. Ultimately, we want to help the community understand how will the characteristic of these extreme events change in the future. So to summarize, this CESM3 and CMIP7, they will be a huge milestone for a climate modeling community. But to the broader community, these milestones only marks the beginning, not the end. In order to make the model information really actionable, we need sustained two-way co-productions. We need to strengthen the roles of intermediaries, and we really need to complement the conventional probabilistic approach with bottom-up storyline approach. Thank you very much.
Wonderful, yeah. Thank you very much, Haiyan. If you could just stay up. We do have time for one quick question, maybe before the next speaker.
If there's no question, I just want to use the last minute to say, hey, for this audience, if you're interested in working on real-world problems, talk to us, please.
We do have time for one quick question. I think Amy had a question.
I was just curious, it seems like the Hurricane Helene is already in progress, but that 6-panel plot, like, is that work already being done? It was your second to last slide.
Oh, thank you so much for asking these questions. Thank you so much for asking the question. The answer is no. We have lots of research papers, technical notes, working on different perspectives of these Hurricane Helene or similar extreme events, but we don't have any effort at national level to synthesize these research results and to translate the result to support decision making. So that's why we need this 5 to 6 pages. It doesn't cost us a lot, but they will really help saving life, saving the economic loss in the future. The numbers we can produce on the computers that can be archived at NCEI, the metrics, they are important. But what are more important are the real life stories that cannot be easily archived, that cannot be easily shared through research papers. Those are the experience that cost money, cost life. That's the effort we're trying to advocate for.
Great point. Well, thanks again, Haiyan. Okay, we're going to switch the order of the next two speakers while we figure out the online option. So I'd like to welcome Suzanne Bauer from Reflective. Hopefully she's here, yes. Welcome. So yeah, Suzanne's going to talk about a story of trade-offs with her reflective simulator for stratospheric aerosol injection. So yeah, thank you very much.
Thank you. It'll come.
We're getting assistance.
Okay.
Suzanne?
Yes. Right. Thank you. Hi, my name is Suzanne, and I want to present to you the reflective simulator for stratospheric aerosol injection and how it tries to communicate trade-offs. So stratospheric aerosol injection, just quickly, is an idea to globally reduce temperatures by injecting aerosols in the stratosphere. And so why do storylines matter for SAI? They matter because the science is dense, as we see in these workshop events, and the public narratives are binary. It's either a climate fix or a disaster. So these are just a couple of examples from recent news outlets. It's a false solution, it's dangerous, it's a possible solution. So these are sort of on the extreme spectrum. But SAI is not a question of like heaven or horror. It's a question of trade-offs. And there's a risk of doing it, there's a risk of not doing it. And so the ultimate question is, which set of risk is smaller? And that's not an easy question, because it does reduce climate change impacts in many regions, but it also worsens the experience in others. And it comes with its own set of risks that are difficult to quantify. And so answering this question is really not straightforward because it's very multidimensional. And also because it has these regionally different impacts, different stakeholders, regions, and different value systems will answer that question differently. And so this is why stratospheric aerosol injection is fundamentally not a problem of, it's not a clear-cut solution, it's a question of trade-offs. And we believe that to successfully communicate these trade-offs, you need to show it, not just state it. And that's why we created this SAI simulator where you can explore these trade-offs yourselves. Before I show you the actual tool, I just want to briefly mention who built it. The effort is led by Reflective. It's a nonprofit organization based in the US, but with contributions from other organizations. And so these are the people that have been involved in it and have done a great job in making it happen. So our main goal with this tool is to build awareness for SAI in non-expert circles. So our main target audience are policymakers and media outlets. And while we obviously want people to draw their own conclusions, there are like 3 takeaways that we really want to make sure are clear. And actually, I'd love your input on whether we're actually successfully communicating that. So the first one is, this technology may become relevant, i.e. climate change is really bad, and there's people thinking about SAI, and it's not just a crazy idea. Second, there are several relevant dimensions when thinking about it, even just in the physical impact sense, such as when, where, and how much. And it's ultimately a question of trade-offs and not a binary perfect solution or absolute disaster. So now I would like to quickly run you through the user interface. So this is our landing page. You get a prompt of whether you'd like more details on SAI, but let's say we're decently SAI savvy and just click Let Me Explore. Then you will be able to choose a background emission scenario and an SAI strategy. So that allows you to sort of create your own storyline about how, when, and why SAI is deployed. And then you can configure the maps to show you the different impact variables. This is a list of impact variables we currently have, but we're continuously expanding this list. And then you have some more advanced settings of like adding significance hashing and so on. And so the output that you see is this map where you can move the toggle in the middle to the left and to the right to see the full map of no SAI or SAI. And you get this line plot that looks at now it's mean temperature compared to pre-industrial. And for the scenario that you can set, you can choose from SSP scenarios for your emissions baseline, and then for SAI, you can choose the location of the injection. So right now it's set to global, but you could choose to just inject in one of the hemispheres or just inject in one latitude band, and the time of deployment and the magnitude. And when you click on edit values directly, you can actually manually select how much you want to inject in which latitude band and in which decade. And so at the top, we've linked a user guide and a document that validates the methodology. And then we also have a bunch of warnings and explainers throughout. So this is just an example, but yeah. So what is the difficult part of communicating trade-offs? The difficult part is that this could be, when you see this map, you might conclude that global mean temperature looks great under SAI. But if you are, let's say, in Southeast Asia and you care about water availability, then you can select the specific region and look at water availability. And then you might say, oopsie, the monsoon weakens with SAI and I got less water, so that's not great. But maybe you think that the most problematic change under climate change is actually maximum temperature that a specific region experiences. So when you look at that, you might say, oh, that looks substantially better under SAI. And so the same scenario can be read in different ways. Global mean temperature looks good, regional water availability looks worse, high temperature exposure looks better. So none of them are wrong, obviously, but which trade-off you care about ultimately decides which scenario looks best to you. And the challenge for us is enabling this sort of free exploration of scenarios and injection types and so on, without letting the user draw verdicts like this is clearly amazing or this is an absolute disaster, but rather think about it, okay, it has advantages and it has disadvantages. And so since we're trying to overcome this challenge step by step, we would love to know what you think, how we're doing so far. So I've created this little feedback thingy. It has only 4 questions. You don't need to type anything in. But while you're filling this out, just a few more words on reflective. Our goal is to facilitate SAI research and to build awareness around this. And so we have this tool, for example, the simulator that I just presented, but we also do other projects. So we have another emulator that's a bit more sophisticated science-wise, which we are going to have 2 presentations also at the CSM workshop. One was in the chemistry session before, and one is in the ML session tomorrow. So if you're interested, I'd highly recommend these. And then we're also providing researchers with resources, be it compute, data, or community around the world. And with that, I'd like you to try the simulator and give me all the feedback you have. Thank you.
Okay, well, thank you, Suzanne. Yeah, I like how you were upfront with your goals of the simulator also. So, okay, we have time for one quick question. You're all busy filling out the survey. John.
We know that climate models are good at some things or okay at some things and not very good at others. In your tool, do you try and communicate that? You mentioned precipitation, for example, and precipitation change. We know they can't really do that right now, even without SAI. The skill there is very, the consistency between models, obviously we can't say how accurate there is very low. How do you get that across in your tool?
Yeah, I think that's one of my main struggles because us as scientists, we're like, well, this is just one model, or there's a huge uncertainty, and so we can add all these like uncertainty bars and significance hatching. But to a policymaker, that doesn't really mean anything. They don't look at like the range of outcomes they see. They just look at the mean line and they interpret that is the true value. So what we do is we actually have these sessions where we run policymakers through the tool and we guide them through it, and that really helps because you learn about how they interpret it and you can sort of direct them in a bit more nuanced direction. This is something I'm actively thinking about, but I don't really have a good solution, because if you just show uncertainty, no policymaker, no non-expert is going to care about it at all. They're just like, well, I can't see anything here. So yeah, I guess I really try to communicate, this has varying consequences and it's complex and, it's not terrible, it's not amazing. Yeah, I guess this is one of my main struggles. If you have an idea, I'd be happy to hear it.
Weather.gov has a weather tool where they do snow forecasts, and they do 10%, by 10% maps. And I find that useful when I'm trying to figure out, what is the range of the snowfall.
Yeah, that's a great idea.
Okay, well, let's thank Suzanne again. Okay, Boulder calling Leipzig. Do we have a connection? Perfect. Okay, I'm very pleased to introduce our next speaker. So Istvan Dunkel from Leipzig University is going to talk about nudged circulation storylines in CESM2. So over to you. Thank you.
Yeah, thanks. Hello, everyone. Very happy to be here. And yeah, my name is Istvan Dunkel. I work at Leipzig University in the field of climate attribution. And more specifically, so we are using CSM2 for something that's called nudge circulation storylines. And we have set up these simulations around a year ago. And since then, several groups have started using these results. So I want to present these, and maybe you find something useful in this approach, and we're happy to give you the data in this case. So a brief start on attribution. So the big overlying question here is we're looking at climate events, and we want to ask how much has climate change contributed to changing this specific event. Now, the problem is that we have very high internal variability, a lot of noise, so it's really difficult to answer this question precisely. Now, what we do, a solution for this is that we can just look at large sample sizes, or this is the traditional approach to solving this problem. We look into large ensembles. But the problem here is that, as also mentioned earlier, when we communicate probabilistic results, this is sometimes difficult to understand, to integrate this knowledge into policies. There's also very high uncertainty due to internal variability, due to circulation, and this also leads to false negatives. So even though we have a climate change signal, we can't see it in the data. So one solution here, or another approach, is this storyline attribution. And here we look, or this is what we call this physically self-contained unfolding of past events, but more on this later. But we reframe the question as, how would this specific event unfold in a world without climate change, or in a world with 2-degree warming, for example? To make it a little bit more concrete, this is what we're doing. So this is our model CSM, and we impose 2 constraints. So A, we limit the internal variability to the reanalysis. So we do this by nudging the horizontal winds. So the internal variability follows the observations. And the second constraint is that we run the simulation on multiple climate forcing levels. So in this talk, we will talk about 3 scenarios, a pre-industrial with natural forcing, historical forcing, and the present day forcing. And so this is what these results might look like. Here we have the 3 scenarios: temperature for one location, And you can see that all of these simulations follow the same internal variability. This is the observed internal variability, but we have the same weather patterns basically, but in different climate scenarios. So we have two climate scenarios with constant climate forcing, and then a historical scenario with a transient forcing that increases in time. And by answering some attribution questions, we notice that there are three big patterns that we find in these results that really help us or really make it easier to communicate attribution questions. And this is what I want to focus here. So one is that with these simulations, we follow the actual observed internal variability. And this is a big plus because often models struggle to reproduce internal variability. So either it's not represented well or we don't see the actual variability as it happens. Second is in traditional attribution, we calculate some delta and we know now we have a warming of 1.8 degrees and then we add this to everything. And here we can really look into individual events and ask the question, how did this specific day change due to climate change? And lastly, with this approach, we don't just look at individual events or individual variables, but we have the whole Earth system simulated with all its processes within one simulation. So we can really deepen our mechanistic understanding of how the thermodynamic forcing changes specific events. The first project we applied this on, we looked into the ongoing European drying. So Europe is a major hotspot of climate change, and we see this mostly in soil moisture. So this is the historical simulation, the blue line of summer soil moisture content. And starting around the 80s, we have this decreasing trend. This is this line. However, the orange line, this shows the world where we don't have climate change, but we have the same circulation patterns, the same sequence of weather that we have in the observations or that we have observed. And even in this scenario, we have the strong decrease in soil moisture. So now we can really partition this trend into the thermodynamics that we understand very well and a dynamic component that is not so small. So in total, we have this 1.6 millimeters of drying in this period, but over half of it is due to circulations. And this introduces a lot of uncertainty because although we understand the thermodynamics, we don't really know how this dynamic change has happened. And we can assume that some of this will reverse, but it's also possible that some of this is forced, so it might continue to strengthen. And with this approach, we're able to separate it, we're able to show what is the actual thermodynamics that we understand, while probabilistic approaches can't really do this. Now, in Europe, we still have the somewhat better case that we can expect the circulation might return. But there's the opposite example. So here we see the dynamical trends in August temperature for the US. And here the dynamics have led to reduction of temperatures. And when we separate this trend now, then we see that in the historical simulation, we don't really have a lot of increase in August temperature, although we have a very strong thermodynamic component. But this is masked by the dynamics. And so this is a way to communicate very clearly that there is this discrepancy between the observed warming rate and what we can expect. And that there is also a very high chance for this reversal. If parts of this is internal variability, we might have a reversal of the circulation trends, which will lead to record shattering events. Lastly, we're also really interested in fire, and with our model, we can simulate burnt area in the Iberian Peninsula really well. And with these historical and natural simulations, we can detect that we have a certain increase in burnt area, but this doesn't answer the full question. We are also interested in understanding really the mechanisms of burnt area trends. And I'm going to skip a bit over this, but basically we're also able to create storylines where we turn off CO2 fertilization so we understand how the increase in fuel availability in this counterfactual world has led to the increase in burned area. So yeah, to summarize, with this approach, we have shown another way to partition the uncertainty. We can really focus on the aspects that we understand. We can create a maybe more intuitive way to represent climate hazards through these storylines, because we're building on the remembrance of recent events on which we can build our knowledge on. And with this method, we're also able to isolate really individual processes, because we simulate everything in this Earth system model, where we can look at the individual factors and processes. So yeah, if you have any questions or you have events that you would like to attribute, please reach out to us. We're happy to share these with you. Yeah, thank you very much.
Okay, fantastic. Thanks very much. Yeah, I see this as a nice advance on like traditional climate change attribution, where typically you're just attributing a single extreme event, whereas what you've done is attributed the entire history of weather over the past 80 years or so. Okay, time for a quick question. So I have a quick question. So one of the motivations for attribution science was in terms of communication. You know, like you just mentioned, it's anchoring climate change in people's experience of an historical event. Have you had any engagement or reactions of how effective this is at advancing people's engagement with climate change science?
No, not yet. I'm also very excited about. So the first papers are just about to be published. We're excited to see what reactions we will trigger, or how the policymakers or stakeholders might engage with this format of attribution results. But yeah, we don't have a lot of experience yet.
Fantastic. You. Okay. Well, thanks again, Istvan. Let's thank Istvan. Okay, well, I'm very pleased to welcome our next speaker, Alison Crimmins from NOAA, who's going to not present another PowerPoint. So over to you.
Thank you. Thanks for having me. I'm Alison Crimmins. Before I get started here, I wanted to note that a lot of what I'm about to show you, the not PowerPoint of my PowerPoint that I'm going to show you, was done by a very large team of writers, GIS experts, web designers, graphic designers. I especially want to call out Sydney Luce as being the key architect of a lot of these story maps that I'm about to show you. So I'm speaking about it, but there's a very large team who was in charge of running these and developing and creating these story maps. So I work in NOAA in the National Centers for Environmental Information, and I lead a program that is partnering with industries to better connect our weather and climate data to the users in those industry sectors. So we're focused on 3 specific industry sectors: the architecture and engineering, the insurance and reinsurance sector, and then the retail sector. And we work with them quite closely. In the federal government, it's one of the better examples or closest examples of co-production, I think, that I have seen, in that we work with these sectors, meet with them, do big brainstorming sessions, try to understand what their data needs are. We then break into smaller working groups, meet regularly with these working groups to prioritize those data needs, and then co-develop different data products and tools to meet those needs. And they are engaged throughout the entire process doing user testing and providing feedback, so that when we get to the end of the line and we have a new data product or tool, they have been very engaged throughout the development process. And these sectors are using them in different ways. They're coming to this process from very different levels of sophistication or knowledge about NOAA data sets. But the idea is that they are using this to make decisions about business operations and to build resilience. I wanted to talk about one element of this work, which is our development of story maps. So NOAA has a lot of data out there, but much of it is inaccessible to people who can benefit from a lot of this data. Either they don't know that the data exists, or they do know about it, but they don't know how to find it, or maybe they find it, but they don't know how to actually use it to make decisions. So people need to know not just where to find this information, but know how to use it. And from a technical standpoint, we address this in a lot of ways, like building tutorials or user guides or data access notebooks or conducting product demos with our teams. But beyond those more technical formats, we also wanted to develop a series of story maps, which are particularly helpful, I think, to people just entering the field or folks who maybe don't have a meteorology background. And so we use Esri's Story Maps tool. It's a web-based platform that integrates text and video, graphics. We are thinking about using these story maps to explain why the data exists, why the data matters, and how the data is being used, which is a way to provide a lot of context to the weather and climate data sets through different storylines. And I have on the right side of the screen here are 4 basic themes that we think about when we're developing these story maps. And so I'm going to show you 4 examples that highlight these 4 themes from our story map. The first one is data access and dissemination. And this is an example of a story map we did that looks at the impacts from hurricanes on supply chains. And I think it really does a good job of breaking down the complexities and building understanding how we use raw data and then embed that data into these use cases so that we are helping people in the retail sector and the insurance sector really understand how to apply the data to their work. And so I'm gonna hope this works. Okay, yay, this is my non-PowerPoint part of the PowerPoint. This is just a little demo of what it looks like to kind of tool through the story map. It showcases the data itself, but also I think the value and the use of the data. And it allows users to interact with historical hurricane tracks as they're making their way through this story map. The second, let me see if I can skip over that. Uh-oh. There we go. Okay, the second theme is science education. So all of our story maps include some form of science information, but we're trying to, as was noted earlier, make some of these complex stories more accessible and to improve understanding of both past and future climate change. This is a story that is looking at one of the costliest severe convective storms outbreaks in the US, called We May Not Be in Kansas Anymore. Let's see if this one plays. Excellent. This is a great story map that introduces a lot of the ingredients of a major storm system and highlights some of the Weather Service and Storm Prediction Center products and forecasts. Okay, our third theme is to develop use cases and applications. And so we're looking to embed real-world stories, real-world applications into these storylines to kind of walk people through the whole process of how someone uses NOAA data to make a decision and then what that outcome looks like. So this is a story map that is describing how NOAA data gets used and integrated into building codes and design standards by civil engineers. This is a fun one because it really highlights the importance of these hand-drawn graphics that our team has done to walk through the different pieces of the story using one piece of infrastructure as an example. And then finally, the last theme is climate and weather impacts. We have 3 really beautiful story maps that are all based out of Alaska. They were developed with a lot of input, both in the text and a lot of the pictures and videos from our Regional Climate Services Director for Alaska, Jessica Cherry. A lot of the videos and photo credits come from Jessie. And one of the things I really like about these 3 story maps is they bring in the voices from local residents. Some of them are actually voice recorded quotes from local residents, and I think it does a great job of weaving together these interconnected disciplines to tell these more complex stories of impacts in very specific places. This is a story map where we have included 3D maps to help illustrate how and why flooding keeps happening in these coastal towns. I think you're going to see a little movement of the map there. Yep. And then it also allows us to introduce some more sciencey, jargony, complex terms like alluvial flooding through these fun, interactive story maps. All right. So those were the 4 examples. There are many more. There's a whole gallery of story maps that you can find. We have a really nice one on Hurricane Helene. What we have found in developing these story maps is that the collaboration is really, really important. As I noted, there's a lot of people involved, writers, graphic designers, GIS folks. And I think this is a really helpful way to demonstrate the use of the data to our industry users, but also to a lot broader audience. And for a lot of folks, this is kind of the gateway into NOAA and understanding what kind of data sets NOAA might have, and hopefully allows them to explore more of our work from there. Thank you very much.
Wonderful. Yes, thank you, Alison. Yes, I like that word gateway. Yeah. Okay, we have time for a question or 2.
So yeah, I really like the story maps. But Esri can be kind of expensive. Do you have any recommendations for things that are like free?
Like other
tools like Shiny or something like that?
I don't, but I can get back to you. I bet our designers have some ideas.
Yeah, this is a really great presentation, and I teach GIS. So my question is it involves a lot of collaboration, right, between writers, subject matter experts, GIS developer, right? So in your view, which part of that can be more automated and improve the efficiency with the help of AI? Otherwise, this,
with the help of AI?
Yes.
Okay. Yeah. Not the graphic designers. I think the artists and the graphic designers are the ones who really bring this to life. And so I wouldn't want you to get rid of those folks. And I wouldn't want you to rob the artists of the joy of creating art by having AI do it for them. So I think you could probably use it in terms of gathering information or thinking through different storylines, but I wouldn't take away either the writing or the drawing elements of it with AI.
You have time?
Yes.
Yeah, so really nice stuff. So who are you serving these things to, and what's the mechanism to get this out in front of?
Yeah, the story maps were developed under the industry proving ground work, which is focused on those 3 sectors I started off with. So you'll see there's a little bit more More of the storylines speak to the retail, the insurance, and the architect and engineering community. But in our gallery, there's an even broader set of story maps. I think they are great education tools as well.
Okay, time for one more.
Hi, yeah, really great talk. I know that like some local national weather service stations also do story maps for other things. Have you like collaborated with them at all, or?
Yeah, we definitely do. We collaborate with different parts of NOAA because a lot of that data is coming from other parts of NOAA. So we involve them in developing these story maps. Maybe we need to make sure they're also in our gallery, though.
Yeah, I was looking, because I've sort of looked at some of those story maps before, and I didn't see any of them in your gallery, and I think some of those are like really, really cool. And I think they definitely add to what
Ooh,
you
maybe
have.
good point. I'm going to see about stealing some of those for our gallery. I
Okay.
mean collaborating.
We'll have to move on, so let's thank Alison again. So I do apologize to everyone and our next speaker for mixing up the order, but I'm very pleased now to welcome Holly Oliveras, who's going to talk about bringing humanity into science.
Hi. I'm a communicator who now does science. And that's me. And no, it's not a frying pan, it's a magnifying glass. I had someone ask me, one of my family members ask me that. I am an ocean biogeochemist, and I look a lot at the exchange of carbon dioxide between the ocean and the atmosphere. And I worked with an illustrator a few years ago who put this together for me as a way to kind of introduce myself to people that don't know who I am and don't know what I study or what it is. A lot of times people are like, what's ocean biogeochemistry? I've never heard of that. Oh, oops. I'm also a mom. So my goal in science is to be human first and scientist second. I say that a lot. I want to bring humanity into science more than we have, and to shift from trust the science to how science can be trustworthy. And let's face it, what we think used to work isn't working for people. For them to be able to know and understand what to do about our irreplaceable habitat. First, most people don't look at charts and graphs and make a connection about how the graph translates to what they can do about climate change. For anyone who's given a talk to non-specialists, you know the first question that comes up is, well, what can I do? And we're not trained to answer that, but we're getting asked that. And so we want to find ways for folks to relate to concepts that we all know and use those concepts to understand what they can do. Second, data and facts don't change people's minds. I did think that when I started grad school here a few years ago, but I'm not passionate about slowing a rapidly changing climate because of data and facts. I'm passionate because of how our changed habitat will impact the people that I love. And I know that you all feel the same. And third, and most of all, no one wants to hear about how bad things are going to get. It's depressing and it's paralyzing, even for me. And so instead, we can get people talking about solutions or what society can be like. So I've been learning for a few years now on the logic behind communication in a way that gets people into motion, into action. And so the old logic in climate change communication was to provide information, and by providing that information, anyone in receipt of it will receive it and know what to do. But this assumes that communication is merely an information transfer. It presumes a one-way flow of communication, as we've heard about today, and it presumes that everyone is already on the same page prior to that communication. And as we all know, everyone is not on the same page about the harm that's being caused to our planet. And a simple example of this would be the information, simple example of the information deficit model would be if a TV meteorologist reports that it's raining. Well, you hear that information and you choose a raincoat to prepare to go outside. A more complex example is to tell audiences of the likelihood of a 2 degrees C increase in global temperature, with an expectation that those receiving the information will know what action to take in response to this news. And another example of the old logic is that climate change is our fault or my fault. And lectures and exhibits like this assume any knowledge gaps are on the side of the public and that that is the root of the problem. So let's get focused on what it is that we're trying to accomplish. One thing is for sure, no matter how someone identifies or how they vote, we all want a safe place to live. We all want healthy friends, family, and communities. Agreed? So how did we get here? Let's take a journey for a few minutes, and I'm going to try and convince you how we got here. I'm going to start with the Yale Program for Climate Change Communication that's been surveying US Americans for about 20 years. Last November, they asked people if they think global warming is happening, and 69% said they think it is. The colors on the map are divided by state, and if they are anything yellow, orange, or red, that means more than 50%, and cool colors mean less than 50%. When the same people were asked if they thought climate change would harm them personally, only 44% said yes. Almost the whole map has gone blue, including Colorado, with all of our climate scientists. So why do people think that they won't be harmed personally by climate change when studies and articles are already showing that we in the United States are being impacted, with some already being harmed by it as it acts as fuel to supercharge floods, droughts, and fires? People are living this. The maps from the Yale program show that we think this only matters to the polar bears and to people far away. But the reality is that climate change is impacting us now. And everyone in this room can agree that Earth's habitat is changing. We'd probably also agree that it's not affecting all communities equally. So let's dig into that a little more. As one example, approximately 71% of African Americans and Black people live in counties in violation of air pollution standards, and that's according to the NAACP Environmental and Climate Justice Program. The latest report says climate change is expected to affect the health of millions of people directly, from enhanced heat waves, floods, and storms, and indirectly by increased smog and ozone in cities, contributing the spread of infectious diseases and reducing the availability of and quality of food and water. We're already there. And this speaks to just one example of the racial systemic injustice that's happening right now in our country. And there are many. But this is something that we can use to motivate us when we're thinking about how to talk about what we study, how to talk about what to do about what we study. And so I'm going to cut right to it. The least polluters cannot change the system to create equity. Surviving takes their focus. I speak from my own experience. And yet 44% of US American adults said they don't think they'll be harmed personally. So where is that disconnect? And how do we shift our collective awareness? How do we make science trustworthy? And this is what I spend a lot of my time thinking about. So I'm going to give you my answer. Realize that our intentions need to be on relationships. No intention but the relationship or relationships, because that is how we create change, is with one another. We are the engine, we are the heart, the soul of how this gets done. And so when you do build the relationships, then amplify the voices and the stories of those who need our help and solutions the most. For those of you that have worked with individuals that are going through hardship, their stories stay with you. Science talks come and go. And so I think that really matters. I think it's important to share their stories and to find ways for them to share their stories. And best of all, if you're not a great storyteller, you can amplify those who are. I did provide some examples of things to talk about. Weird weather. flowers and trees blooming earlier, spring starting earlier, et cetera, et cetera. I don't really use the term climate change anymore, except when I'm talking to scientists. I talk a lot about our habitat and centering our habitat in our decision making. Also, you can think about your climate change aha story. Mine began after overhearing a conversation in a grocery store where I heard someone say it's more like global weirding. And I thought that was really clever. And within a couple of weeks, I went home and Googled it. And who did I find but Katharine Hayhoe with her short videos that answer one question about climate change. I started sharing them on Facebook. And within about 6 months, my own friends and family were DMing me with questions about climate change. And I had no idea. But that's how it started. And the person in the grocery store will never know what an impact she had on my life. I wasn't even the customer. I was just in line. Also, think about your why. People don't make lifestyle changes because of data and facts, but they do when their heart is involved, when their identity is involved, when their values are involved. Yes, these are my kids. Think local. When I first started grad school here in Boulder, I wanted to be the next Katharine Hayhoe and have a huge social media following. And over the years, I've discovered it doesn't do me much good to have a great big following if I don't even know my neighbors. And so I decided to focus locally and get involved with local government and the school boards, et cetera, my local communities that need help today, right now. And what an incredible position to be in, to use my position as a scientist and be in communication with people that really need help today. It makes a big difference. So final words, find your unique way to help others get talking about climate change, especially when it comes to racial injustice and climate injustice. They are connected, and I'm happy to talk about this for hours. Weave hope and solutions into your message. We need to talk about what life can be like. I often say it's like rock climbing. You can't let go of one hand until your other hand is secure somewhere. And if all we're talking about is how bad it's going to get, we're not going to feel safe or secure to try that new thing or to change our lifestyle or to meet some new people, to try new things. Amplify the voices of those impacted most. Talk about centering our habitat in your decisions. And that's it. Bye-bye.
Wonderful. Yes, thank you very much, Holly. We have time for one or two comments or questions. So I wanted to pick up on something you said. You said if you, I'm paraphrasing, if you're not good at storytelling, you can support those who are. So could you comment on whose job it is to do the storytelling?
Oh, well, for me, it's the people that are living through these experiences. Mm-hmm. Their own stories are moving, they're powerful in all circumstances, good, bad, and ugly.
So just a quick follow-up then. So what's the role of scientists in that storytelling?
Oh, yeah. So I often say, people actually really don't care what I do in my day job, right? But they know I'm a scientist and they know I understand. And if I'm available to make that human connection, then there's going to be some trust there. And I have learned the hard way many times, I can't sell climate change. And I can't sell behavior change. It's not going to happen. But I'm living it. I'm living it myself, right? And so I think that's a big piece. I had a comment actually to Stephanie about the uncertainty conversation. The analogy that I use is an artist. If you went to an art show and the artist was in front of, say, a painting, and you got the chance to talk to the artist, and they're telling you all about their piece of art, what the message is, the feeling, right? I don't need to expand, you've been there. They never talk about what kind of paintbrushes they used, or if they got this paintbrush on sale, or this other paintbrush had this weird little piece sticking out and it made this cool line. We never hear about those things. We never hear that that canvas has been painted on 6 times, right? We hear about the message. But as scientists, because we want to have integrity, we want to be objective, we want to share, be transparent with one another, we are in that habit of talking about uncertainty. It's what we talk about, and for good reason when we're in this environment. But when we're talking to non-specialists, as you were kind of alluding to, it's what is the message? And so I'm excited to talk to you more about that too.
Yeah, thank you. Dave.
Yeah, so you said right at the end here that nobody cares about what your day job is. We all care about our day jobs.
Yes, we do.
And if we're talking to people, we probably somehow we want to fold our day jobs into that, into our discussion. If it is the climate change issue or the environmental change issue that we're trying to talk about. So, what if you have any thoughts about how, or do you try to fold that in at all? Because I'll say in my experience, I don't do a ton of, communication necessarily, but when I have, I've sometimes taken the approach of talking about how, less about like the facts, but how we got to some sort of scientific understanding. And in our case, we're building Earth system models. And I actually find people kind of engaged in that. I'm probably preaching to the choir audiences, around Boulder or something like that. But I'm just curious if you have any perspective about that.
I was going to say that. We're probably in different circles. In my personal life, I'm not in circles of people with PhDs who study the climate system. They're not really concerned with where I got my education or what I do on the day-to-day. And for me, my research is in the ocean. There's no people there. It's really difficult to find that connection. But conveying in ways that show I understand how the Earth system works and how the climate system works, and that I understand what we're headed towards is going to be bad unless we make change. But I've gotten a lot more specific about that too. When I first started 10 years ago, I was talking about shower lengths and recycling and composting, right? Which those things are important because they're getting us in that habit of making change. But now what I'm talking about are the big polluters, and that we don't have to be angry, we don't have to blame anyone, but we know better now, we need to do better now. And it's really on all of us to be the collective voice to say, we know better, let's do better. And so, yes, we're going to get into some deeper conversations about our value system, right? And none of that is part of my training as a scientist. And so that's where I keep coming back to that human first, scientist second. Hopefully that helps.
Okay, one more quick question.
Okay, yeah, I'll try to make it quick. Thank you. That was a really beautiful talk. I think you're absolutely right that a more effective way to communicate to people who aren't specialists is to appeal to how it will affect them personally, their values and loved ones and so on. I think you're absolutely right, but what I struggle with is how do you strike the balance between doing that without feeling like you're trying to emotionally manipulate them or sensationalize the impacts. That's maybe a bit harsh way of putting it, but how do you make that balance? Thank you.
I completely understand. Yeah, I mean, my own family has said, 10 years ago, could you stop? We just want to make brownies. Do we have to talk about where the oil came from? But I have become a fun little encyclopedia of facts. Did you know that paper towels come from the boreal forest in Canada? The day I learned that, I decided I don't need paper towels. I need those trees. Another one was in the grocery store. This was years ago, but there was a hurricane on the East Coast, and about 30,000 pigs were wiped out. And I grew up in New Mexico, and I was at the grocery store, and the person next to me said, the price of pork has gone up 3 times in the last 2 weeks. And I said, I think it has something to do with that hurricane that was on the East Coast. And she's like, whoa, I never thought of that. And that was the end of the conversation. I stopped trying to convince, stopped trying to show them how much I know or how good I am at convincing, any of that. It's just dropping something here or there, like the gal that said global weirding and got my ear. And so I just trust that that's enough and that I'll never know the ripple effect of my own behavior. But it does feel a lot better than me trying to convince people and failing, because I've tried that a lot.
All right, well, yeah, let's thank Holly again. I'm pleased to welcome Kristen Krumphart, who's from NSF NCAR. So Kristen's going to be talking about using art for climate change communication. So thank you.
You are. Okay.
Oh.
Oh.
Hi, everyone. So yeah, my name is Kristen Krumhart, and I'm a scientist here at NCAR. And I just want to start off by thanking the organizers for letting me speak here today about communicating communicating science through art. And this is the first time I've ever really given a talk about this, so this should be fun. But I thought I'd start with just my story about art and science. And basically, I've always liked both and kind of struggled between the two, especially when choosing a major in college or something like that. I went from being graphic design to art, and then finally settled, luckily at Iowa State. They had this biological illustration undergrad or major, and so that's what I did. And some of these illustrations here are some of the ones I did when I was there. But then since college, I kind of took a science-focused career path, and instead of being a science illustrator officially, I just looked for ways to bring my art into my science. And so in this talk, I'm just going to talk about like different ways that I do that, and going from using art to kind of communicate science to actually using art to do my science. So I thought I'd start with, this is the very first illustration I had in a scientific publication. I was culturing some phytoplankton in the laboratory under these really controlled settings, and I designed this culturing system. And rather than showing that picture to the left, I drew this diagram. In the publication, they're all labeled and everything, but it really helped to explain the system for culturing phytoplankton. And you can see the phytoplankton in the little vessels right there. So next, I was going to show another way to get my art in my science. Is I discovered that whenever you get a scientific publication, you can supply some cover art. And so these are some examples of some cover art that I did. And so if we look at this one, it's like I got when I brought the coccolithophores, which are a kind of phytoplankton that make these calcium carbonate shells, and I put them into CESM. That was on the cover there in James, and then and I just wanted to point out all of these use CESM, so it's like obviously a very inspirational model. And this other one was based on the CSM1 decadal prediction large ensemble, and I just wanted to kind of convey how variable the ocean could be and how we can predict that in some regions. And then this one on the right, that's a pteropod shown that I painted there. And that one was looking at ocean acidification, because pteropods are really sensitive to ocean acidification. And we were looking at that in the Southern Ocean using the CSM1 large ensemble. Another example is just to put my artwork on a science plot. And so this is like when I was building that parameterization for coccolithophores. This is a big meta-analysis that I did. And I used my illustrations of the different coccolithophores to communicate how big they are relative to each other, and then also just how their morphological diversity. And they're like super, it doesn't show up so well, but they're really beautiful phytoplankton. So I was lucky to study them and draw them. And then another one is to explain the methods of science. And so this is an example of that. And this is from a paper a few years ago where I hooked a CSM up to a fish model called Feisty. And so this just kind of helped to communicate all these different relationships between the different parts of the ocean ecosystem. And like the mesozooplankton group is the food for some of these fish types here. And then I use different color arrows to communicate growth from one size class to the next of the fish, and then reproduction in the red. And the black arrows are all like different trophic relationships, so who's eating who, basically. And the fish one is down here. It's too complicated to put up here. So that's another example. And then I also use artwork to explain results. And this example is, I was basically, I was looking at time of emergence in across different components of the Antarctic ecosystem, and from sea ice all the way up through penguins. And so basically I took all these plots that show time of emergence with these little dots on the line plots, but that's like really hard to see what's going on, basically. So instead I synthesized that into something that communicates a lot better to put those time of emergence on timelines and whether they're increasing or decreasing with time. And so that's another example. And so I just did a lot of little illustrations of the parts of the ecosystem that I was modeling. And this one's based in the CESM2 large ensemble. So this is moving on to actually doing science with the art. And so this is a study that we did with national marine sanctuaries and bringing ocean climate projections to stakeholders in national marine sanctuaries. So these could be the sanctuary managers or like people who own a tourist shop or do diving or fishing or anything like that. And so with this one, this is based on the Flower Garden Banks National Marine Sanctuary, and that's deep water corals in the Gulf of Mexico. And we're kind of, there's a big social science component to this project, and they're going to interview the social scientists on the project to interview all these stakeholders. And so they used my illustrations here to kind of communicate what the climate change meant for their particular ecosystem. So I had to do a little bit of research on this. Like these boulder corals here are really sensitive to ocean warming and ocean acidification. And so, they got a lot smaller with climate change. Also, our fish model that I kind of described a few slides ago showed a big decrease in fish in the region. And so that's kind of communicated. And so, yeah, we brought these to different stakeholders, and then that really helped to kind of communicate what that meant to them and get them talking about some of the climate change, the potential climate change impacts from those changes that were predicted by the CESM2 large ensemble. And then the final example I'll talk about is this Rising Voices Changing Coasts, the RVCC project that we have. And this is a collaboration between our system scientists and Indigenous knowledge holders, and there's different regional hubs, but my work here on this one is focused on the Alaska hub. And this is a challenging project for many reasons, but one of the reasons is they think like these Indigenous knowledge holders, they think very local in scale. They have a really intimate connection with their environment, whereas us climate scientists tend to think kind of larger scale or regional scales. And so I wanted to look at the changes that we're seeing in the ecosystem in the CESM2 large ensemble for this Bering Strait region. But it is still just really hard to communicate and see what people would care about. So I decided to learn about their marine ecosystem by drawing it and then use that to start the conversation. And so this is my first sketch of the Bering Strait ecosystem. And basically I took this and I just put what I thought would be important based on a few kind of preliminary conversations. And then we took a trip up to Shishmaref, Alaska, which is, well, it's kind of hard to see on these maps, but it's on the Seaward Peninsula right here on the South Chukchi Sea. And I also had all these plots that I had made with the CESM2 large ensemble saying how things might change, and either it was I just simplified it with increase or decrease or a shift in the seasonal cycle, which was shown by these icons around the edges of this poster that I brought up there. And then I just wanted to use it and see what they thought, and I got a lot of feedback about this, and it really did help to start the conversation. I just wanted to acknowledge the elder Johnson, who provided all the Inupiaq translations on this, and he also provided just a lot of feedback on the ecosystem changes. And I just got a lot of anecdotes about different parts of the illustration and what people thought were changing or things I was missing. And we also hold these collaborator meetings over Zoom too, with the different elders around the Bering Strait that have helped kind of further this process along. So yeah, like I said, I got many suggestions on what to add or change. And so now I'm working, this is very much a work in progress, but I'm working on the final version of this. And some of the suggestions were more Indigenous activities, like this is a skin boat, fish camp, which they do every summer. So there's seal hunting, and this is ice fishing, which I saw when I was in Shishmaref. And then they wanted more migratory birds, so I added a lot, and I really like birds, so that was a fun one for me to draw. And all these are like, you could, so rather than the first sketch, it was all like all in one piece of paper, where this is now all, they're all separate, so I can really move them around, and we could zoom in on different creatures. Also, they talked all about harmful algal blooms. One suggestion I had, which I think was really nice, was to integrate more of a seasonal perspective. So I have these like seasons, like in different subsistence activities that they do. And also they wanted me to incorporate rivers, because it's not just the marine sources that matter, it's like where the rivers enter the ocean as well. So I did that. Yeah, so I think that's it, yes.
Yeah, fantastic. Yeah, thanks very much, Kristen. Time for one quick question. So I had a quick question about when you use art in your publications. Do you have a sense of whether there's like more engagement in your scientific publications through like maybe citations or other measures?
No, I guess I just always do it, so I don't know what would happen otherwise, but the reviewers do seem to like them.
I mean, you're on the front cover. You're on the front cover, so
yeah.
Okay, fantastic. Yeah, let's thank Kristen again. Okay, we have one final talk before the break. Who is, nope, okay. Okay, so that was the last presentation. So we have 10 more minutes. He's not available? Okay, okay. We might try and catch the last speaker during the break. But yeah, so we have 10 more minutes for any burning questions from all of the talks. We had a bit of a buffer. So I'll open it up to anyone who didn't get a chance to speak earlier. Christine, please.
Thank you to all the speakers. It was all wonderful. This is a little bit of a philosophical question or maybe discussion. I heard a few places where we talked about message is the most important thing, and we somehow have to figure out a way to not confuse people with uncertainty. Maybe that's not what I don't know. The uncertainty question and the message question are two sort of things. How do we combine them? But my question is a lot of what we do, the uncertainty is actually the message. So how do we not talk about uncertainty when that is actually the message? Speakers.
Great question. Holly is brave.
Well, I was going to steal from Catherine Hayhoe once again. She says, we don't know everything there is to know about gravity, but we know enough to stay away from the edge of a cliff, right? And so I think, again, I appreciate David's point. It depends on the circles that you're in. But certainly I think we do know enough. And when we get to talking about uncertainty, my answers are, models are a tool in our toolbox. We know as best as we can, and we're learning more every day. And if you'd like to join us, please do.
Thank you, Holly. Any other reactions to Christine's comment? Over to Alison.
Thanks. I kind of wanted to connect a few things here, but I really love that last talk on art. When we did the 5th National Climate Assessment, we did our first ever national call for art, and it was such a beautiful way to bring in new perspectives and emotions and different ways of understanding climate change through the art. And I loved what you said about as a student being, struggling with that, should I be a scientist, should I be an artist? Because a lot of the feedback we got from students were like, well, I either have to be this or that. And so we try to tell them, you don't have to choose. You can do all of those things. And then to the question about, the Esri story maps being expensive, and are there other formats? I've been thinking about this, and then during some of the other presentations, thinking about how to make it more connected to people and how to make it more conversational and how to put the people first. And I think one nice thing that this is a weird thing to say, but the one nice thing about TikTok uh, is they're not like, the story maps are kind of slick, right? They're fancy, but like people don't expect that on videos, on Instagram, on TikTok. And so I think you can get at some of that human element when you use some of those other types of medium.
Thank you, Alison. Over to Kevin.
Just had another thing to consider in the context of Christine's question, and that's sometimes it's helpful to just put the uncertainty in context. You might make yourself appear more honest and be able to connect with people by saying, we don't know everything about this, but consider the people who pretend to know everything about something. What are they trying to do? They're doing something for themselves. I'm trying to do something for all of us by communicating what we know and what we don't quite know. So sometimes that's helpful.
Yeah, thank you. Yes, we have another remark.
First, thank you to all the presenters. I thought they were all really lovely presentations. I think another hurdle to storytelling, especially right now, is kind of the proliferation of disinformation. I think that's something that I've encountered while trying to communicate things about the climate to loved ones, family members, just people of different backgrounds. So I'd be curious to hear folks' strategies for helping kind of bridge that. I don't want to call it a gap, but like address that, I guess.
Great point. Any immediate reactions to that? If not, I'm going to leave that as a thought for us all during the break. And maybe that could be a starting point when we return. So after the break, we'll all be in this room for 15 minutes to continue the synthesis of what we just heard, talking about commonalities and differences in the formats and goals of storytelling. And then we'll move into breakout. Some more details on that when you come back in the room. So yes, let's thank all our speakers again for a great set of talks.
Test, test. to create your own stories. So before I get going, I'm going to introduce you to my lovely colleagues from SciEd, Tim Barnes and Katie Wilson, who run a SciComm workshop to help people like us learn how to communicate to real people. I'm going to let them try and explain, and then I'll talk a bit more after.
Cool. Sure. Tim and I are going to float around with microphones. Hi, everyone. I'm Katie Wolfson, she, her. I am the School and Public Programs Manager with the UCAR Center for Science Education, or SciEd. And so my kind of background and why I'm here with Tim is that I used to do botany research and biology research, and then realized that my love of science came from being at my local nature center and through museums and science centers and things like that. And so I realized that I actually love learning about science, and I love doing science, and I also love talking to people about science. So I kind of went into that science communication route and did my master's at CU Boulder in museum and field studies, focusing on public attitudes towards science. And so now I work at UCAR. We help run all the field trips and the tours, and we get to develop those programs. And it's a lot of fun talking to audiences from preschoolers to Speaker of the House, Nancy Pelosi, when she comes through. So all sorts of audiences we talk to. And I have the pleasure of working with the wonderful Tim, who some of you might have met before.
Thanks, whoa, hello, that's a little hot. So I've been doing interaction with the public for the last 30 years at the Mesa Lab doing science communication. So we were really excited to be here doing that work. And my background is, my degree is in communication from the University of Colorado Boulder. Prior to that, I did a stint in the US Navy with fighter aircraft working on technical systems. And then I switched over something, the natural transition to child psychology intervention. So yeah, so there we go. But I think part of the really important piece is I can tell you there are people who are waiting to hear you speak about your work. So I'm so super glad to be here today.
Yeah, I think that's one reason that Tim and I don't love the work that we do, but getting opportunities like this to come talk to folks, because there's so much amazing work that y'all do and stories you have to tell. And voices you can amplify and help and connect with your audience. And so hopefully today, we're gonna spend this first little bit kind of reflecting back on what are some of the themes that we saw across all the wonderful presentations just a little while ago. And then see if there are any themes that we missed that y'all also wanna call out or discuss. And then we're gonna switch gears to kind of a hands-on breakout session. And I promise it's not too scary, so I hope you'll stay and do it with us. And just to kind of go through the practice of starting to think about things that like audience and storytelling techniques and story ingredients. And then maybe do a little, dabbling in creating something and then reflecting back on what that process was like for you. All right. And for those of you online, we're going to have an online option for that as well. So Tim, what did we hear earlier?
We heard something very important is to know your audience, and more attuned to that is identify your audience. And that's something critical to do. I think a lot of you recognize that. And the better idea you have of who it is with whom you're speaking or interacting or doing your art or interpretive dance, which I hope somebody here goes for that, then you'll be able to communicate the message better if you identify them.
Yeah, and I think too, like that word audience too, I heard it, a lot of different variations of that word. I summarize it as audience, but I heard stakeholders, users, community members, probably some other ones that I'm forgetting right now, but there are different words that people used, but kind of you think about it of like, who is your audience that you're telling your story to or creating a tool that tells a story for, right? And that's gonna have a huge impact on then your message or your key takeaway that you want that person to have, because you don't need the same message for every single audience. You shouldn't have the same message for every audience. Anything else on that key message, Tim?
I would just say that your colleagues are also an audience, and that might be that they are not expert in your area. So when you're creating, you really need to consider like how much are they versed in the work that you do, and keep in mind, you may identify an audience by demographics, but they might have a level of information that you're not aware of. So they might not be familiar at all with earth system science, or they might be 5-year-olds and very versed. So careful with the 5-year-olds.
That happened at Mesa Lab today. The 5-year-olds on a field trip today had awesome answers for why the sun mattered. So, so yeah, and I think that key message too of being mindful that there's lots of different ways you can deliver a key message, right? And focusing on like, especially, you know, Holly, you touched on like kind of avoiding that doom and gloom messaging and just focusing on that of like, where are those messages of hope and resilience and things like that? Or how does your key message connect with your audience's values, right? So it's not just about here's the exact data, but what are the shared values or maybe these more universal themes like safety and family and love and things like that, that people might connect to, that you can incorporate those into your key message and make it a really strong key message if you're connecting to those values that your audience has.
Can I answer that?
Yeah.
The importance of staying on your key message is I can't be overstated. And an example, I was able to see one of your colleagues interviewed, and UCAR Communications helped them get through that. But the interviewer tried to steer the interview to a different place. But the scientist came back on topic and kept going. And that's a completely different realm of communicating, and UCAR Communications will help you get through that. But even in that case, it was like, stay on their message. We're talking about this right now. You don't have to be condescending, but
yeah, and I think your key message, if it connects to your goal of your communication too, right? I saw in multiple presentations today of like, our goal with this tool or this story was this, right? And so if you have a clear idea of what your goal is, that also helps you focus your key message in really well for that. Another thing I saw was that there were tons of different formats, mediums, ways of telling a story, right? We saw things earlier today about interactive simulations. We saw talks and presentations of how you might frame that. We saw things about artwork that tells a story. So there's so many different methods that you can do it. Also, I know in the resources folder that there's a link to coming up has some lists of things that are other formats like interpretive dance. If anyone's heard of Dance Your PhD or Dance Your Thesis, the team who put together this session found some of those if you need some inspiration of something a little bit different than maybe you've done before. You don't have to dance today, it's okay. If you want to, go for it. So there's lots of different formats and mediums for storytelling. And so being mindful of what format you're choosing and which one you have skills in, and which one your community or your audience is going to connect with, and how they tell stories too, because not everybody tells stories the same way. So there's a lot of variation across cultures, across countries, across professions about how we communicate stories. So whatever you can do to learn about that is amazing and will make you a better communicator for that.
And the be yourself piece on here, take that to heart, because there are different, we all excel, and use your talent to do that. And because you may be speaking to a culture that's very different from the one from which you came, and that could be, there's all kinds of different cultures, right? So language is one piece, culture is another piece. So if you speak the language and you know the culture, go with that piece and figure out how to work through those. But definitely be who you are. The authenticity will show.
Yeah, and be yourself can kind of be, bringing that human first side of you, right? Like other aspects, which I realized Tim and I didn't do that, and beyond our career paths and things like that, that I also do filmmaking on the side. I'm a mom of 2 kids, right? I grew up in the deep South, but I live out here in Colorado now. There's all these different aspects of things that you can bring into your storytelling. Like I teach a lot to kids about hurricanes and developed hurricane virtual field trip. That's really popular. James helped consult on that with us. It's our most popular virtual field trip, but that one, I get to reference my growing up in Southern Louisiana, where I didn't have snow days, but I had hurricane days, right? And so that's a way that I can kind of bring my authentic self into my storytelling when I'm teaching that program to kids. And so being yourself and being human with your audience is really powerful. And then also being yourself in that, like, if you don't have to come up and be a stand-up comedian to connect with a non-expert audience over science. Some people do that, and that's great. If that's you, run with it. That's amazing. If you're an artist, right? Like if you want to bring your art into all of your research papers, right? That's a beautiful thing to bring to it. If you are a programmer and you want to bring in your programming skills or developing cool interactives or coding or things like that, right? Being yourself is also bringing your own skills and your own passions to accomplish what you want to. Oh, our slides went away. What was our last one?
Yeah.
Let's
not
see.
gonna get any help with there.
There it is.
Collaboration matters.
Oh, and people first.
Oh, people first.
And the stories you amplify.
Right. Remember the stories that inspired you in your research, and then if you get stories of who your audience is, feel free to incorporate those. Make sure you understand the story and the impact of that story. But letting your audience know that, for example, there are other people who are struggling with the same thing you struggle with in your science. Share that. And if you know of like a high resolution story, high resolution, bad idea. I'm thinking the next door. But if you have something with a lot of details in that, relay that into the work that you're doing. Let them know that you understand who they are and how significant the impacts are of what they're experiencing.
Yeah, it's great. And then one of our next ones was collaboration is really powerful, right? And so that could be collaborating with the communities that you're serving, that you're working with, that you're telling stories with. So hopefully you're telling stories with them and not at them or for them, right? So that collaboration with your audience, it's always, I heard actually a lot in the talks of people talking about it being a two-way exchange of information. This is a common thing that, I came across in like museums and other science communication things where your audience is bringing their own set of experiences to whatever you're also bringing to share with them, right? So it's always going to be two-way in communication, no matter what format you're doing. And so if you can think of that as a collaboration in that two-way communication of how do you get, again, to that key message or your goal with that two-way communication. Also, collaboration, I heard a lot in the presentations too about different disciplines and professions and skill sets coming in to tell a story, right? Having writers, having GIS, having graphic designers on those Esri story maps, right? Of having that kind of interdisciplinary team. So you can collaborate, within your own department or things like that, but then also collaborating with artists and communicators and writers and community members can make your story that much more powerful and meaningful and relevant, which I think is our last one.
Yes, and relevance is just that. And timing is everything. And the more you communicate with those around you, you'll understand where you could share your information. If there's a workshop, like that's why we're here. Hey, this could be relevant. And then that's where you remember all the pieces above and when you deliver that message. And I heard along the way, people mention policy. So I have to share with you, I am an elected official and the imposter syndrome is just oozing for me because there are people who want to know what you know. I do my best, but I can guarantee you if there's an opportunity for your local representative, to work with them, they will love that work. If your message is clear, they can get in. And there's a lot of relevance right now, and I'm going to stop right there. But there are a lot of things that you can do as soon as people understand that you have access. You might not know everything that they're interested in, but you have access to some of those bits and pieces.
Yeah. So how can you make what you're working on relevant to them? Right? And personal, right? Whether it's their own experience or someone else's. Even if it's someone else's experience or another story that maybe they haven't experienced personally, you can still make that relevant through the storytelling techniques that you use. So is there anything there that we've missed that you heard in the talks earlier or things that you think are important to highlight or that you have had experience with in your storytelling or communication? I just want to give a shout out again to the presentations. And yeah, Holly, come on up. Because yeah, Tim and I were frantically taking notes. We didn't hear these presentations beforehand. So
I was just going to say the feedback that I heard while we were on break was that we need to be having these conversations more often in the scientific communities. And so I'm really grateful for this session, and thank you both for being here.
Thank you, Holly. And thank you everyone for being here in this room right now, because I think that speaks volumes too, and how many folks were in the talks earlier too, to, you know, the desire and the value of how we're kind of valuing this type of communication in the scientific fields in the community. I think is really, really powerful.
And some of you, Holly mentioned Catherine Hayhoe. If you haven't seen the way she works, and Raj Panja, maybe some of you met him long ago, but he said clearly, if there's someone, if you're trying to understand how to deliver, how to communicate with others, find somebody that does it well and copy their style, not their words, but their style or their, you know, their art or whatever. Catherine Hayhoe is a great model. And she is a mom. She's also, it lives in oil country. She is married to a man of the cloth. She's Canadian. So there's a lot of different things that she can bring to the table that make it great for her, you know, to look at some of the ways, the different ways that she does her work.
Yeah. All right. So I think we're going to move on to doing some hands-on practice now with this. So for this, let's go and switch to our next slide, Jesse. Thank you. So for this storytelling activity, we're going to kind of break out into little groups. We can stay in this room. You can also go out to the tables if you want to. Mari brought some wonderful materials if you want feeling kind of crafty and want to do some drawing or art or writing or things like that. But what we're going to do is we have some of our facilitators, I believe Holly and Kristen might help us with this. If any of our other presenters wanted to come up and help too. Oh, Allison as well. Awesome. So actually, I'm going to have our facilitators kind of come up here because then we can divide up our groups based on how many we have. But what we're going to do is we're going to break up into smaller groups. And for those first 5 minutes in your group, what you're going to do is you're going to think about a topic that you want to work on telling a story about today. Right? Could be your research, could be talking more broadly about a topic or things like that. And then everybody can grab a copy of, there's the little kind of storytelling guide. And this QR code goes to a digital copy if you prefer typing things versus writing things. But then you're going to, once you're in your small groups, you're going to find a partner to interview. And you're going to interview them and ask them, what's your topic? Who's your audience? And then there's some different prompts there to how to think about audience. Why should your audience care about this story? What do you want your audience to walk away thinking, feeling, knowing, or doing? And then some format brainstorm. What's the medium? Are you doing interpretive dance? Are you doing a talk? Are you doing a hands-on classroom activity? Are you doing a poem? Are you doing a scientific illustration? Are you developing an interactive model or tool? Are you doing a story map, right? So what's kind of the formats you could use, and then circle the one that you want to work on today. Okay, so think of something, choose one in the end that you can kind of workshop or outline or things today. Okay, so you're going to basically work with a partner to interview each other to answer those questions. Then you're going to find a new partner and flip it over to the other side. And there's kind of helping identify, you're going to interview yourself to find your storytelling ingredients. So thinking about, you know, is there tension or mystery you can do? Is there a beginning, middle, and end to a story? Are there characters in your story? Are there sensory details that you can bring in? So there's some guiding questions there that you can interview each other to see, what are you working with? What are your ingredients? Okay. Then, so that'll be about 25-ish, 30 minutes. For that. There's some times on here, facilitators, but we're already running behind, so you can just kind of tweak them. And then we're going to have about 15, 20 minutes then where you can just kind of work on stuff. You can outline stuff on pen and paper. You can craft with the materials in the back. And then what we would love at 4:30 is for people to come back in the room. We don't have to do it as a big group with everybody coming up and presenting. We can still kind of stay in our small groups, but come back in this room at 4:30 and then kind of in your little small groups, talk about what that experience was like. Maybe show off what you made over that 15 to 20 minutes of what you got started. But just kind of reflecting as a group on what that process was like and what kind of came up for you doing that. Okay. Does that make sense, facilitators? Okay. Instructions for on, yes, thank you.
So I'll just add for the online folks, if you have a look at the email that Elizabeth sent out with information about this session today, that's got a bunch of links in there with access to the same Google Drive and all of the resources. It's also got a link to a Google Meet. And we've created breakout groups so you can join the Google Meet and we can switch you up if you want to go between a couple of different groups, and we'll do the same process. Again, you're not obliged to present to everybody. We can just keep it within the online community. And also big thank you to all of the admin staff who also helped collate. So there's a jumble of stuff over there. The things that are more kid oriented are the stickers. That's more of the stuff I brought, and then the other things the admin team brought, and it's yeah. So if you want to go arty, we've got the tools for you.
All right. For those of us in the room, I'm going to pull out some of my classroom techniques now for how we're going to divide up into 4 groups. We're going to have we have 4 presenters, so we're going to start with 4 groups. So Melissa will be group 1, Kristen will be group 2, Holly group 3, Allison group 4. Okay. And then we're going to go around the room and we're going to count off 1 through 4. And that's how we're going to divide it up. Okay. Laura, are you going to go in a group or? Okay, perfect. You're doing online. So Kevin, why don't you start with number 1? It's scary. It'll be easy and fun. Yeah, thank you. wrap up. If anyone has something you made that you want to show off, you can. But otherwise, we're just going to kind of share out and kind of reflect on how that was for everybody. Any kind of ahas, any things that were really hard, anything that it made you think about, or a takeaway you might have from today, from the talks earlier, or from this activity. So everyone seemed super engaged when I walked by. So thank y'all for participating in that. Tim, also apologies. He has to go communicate and do a city council meeting right now. So he had to take off a little bit early. But he was really excited and grateful to be here today. So we might have one more group outside that's making its way back. But just to kick us off, anybody want to share how was that for you and your group, or any takeaways or anything like that? And we can pass mics around too. We're just recording it for other stuff. But yeah, Cecile.
Yeah, then when you proposed the activity, I was not completely convinced that to have a partner would be useful. And I found it was really good. It was really with this interaction, because I was thinking with a suite of questions that I can answer myself. I don't know the other, but I found this really, really good. We really did a lot of progress, both on our story, my partner was Cheryl, by having a partner. And I don't know if you were expecting this, but
I was the same way. It's like, do I leave before this? Because I don't think I'll get anything useful out of it. But it opened up some ideas that I hadn't even thought about just by talking it out with somebody, getting feedback. And it's like, oh, that makes me think about doing this. And yeah, the interaction helped me to fine tune something that I didn't even think I was going to do. So.
Awesome. How about for everybody else? How is it having partners and interviews and conversations? Overall thumbs up. It's okay if it's a thumbs down too, but lots of thumbs up, I'm saying. Awesome. Yeah, and I think that kind of ties back, right, to thinking back to that storytelling theme, that collaboration of how that can be a really powerful tool, right? And so whether that's a peer or your audience or a different person with a different set of skills or perspective, bringing that to and just talking through that with them, I think can be eye-opening and lead you to different places. Yeah, Kevin.
Yeah, I found having a partner in these discussions was really excellent as the brainstorming stage. And it made my idea and turn into a project, which I realized I didn't really want. I wanted it something like small and focused. So I'm gonna have to go back and process all of the thoughts and focus and, toss some out and actually make it what I had in mind to begin with.
Anybody else? Anybody worked on a project like that other times where you've started working with other people and suddenly it snowballs into a bigger? Is that Mike? I think it was working.
Is it working?
Could
Yes.
folks hear Kevin? Okay.
I wasn't close enough. Sorry.
Yeah, so Kevin started with an idea, worked with a partner, and then it got much bigger into a full project than just a particular concept, and having to reel that back into the scope, right? So I feel like we've probably done that in all our careers and different projects and things beyond just communication. But I think, again, thinking back to what's your goal, right, for it, and kind of having that goal to reprioritize and recenter yourself can be really helpful for that too. For those of you who are just joining, we're just doing kind of informal discussion about if you have anything you want to share, you're welcome to, but just kind of like, what was that experience like for you? Do you have any aha moments, challenging moments, takeaways that you might have? And that can be takeaways from the talks earlier too. Anybody else want to share a little bit what the experience was like? Anything that was surprising or hard or?
Yeah, it helped clarify for me what it is I'm actually trying to communicate. Just talking it through with someone, and so it made me understand on a deeper level why I'm doing what I'm doing and what it is I want to communicate.
Anybody else connect to your why a little bit, or force to connect your why? Yeah.
I think a kind of common through line from our discussion was that it can be useful to kind of center vulnerability in your why when you're communicating your science to people. Just because I think centering the human aspect of it kind of brings people in and, you know, wants to have them in conversation with you. So.
Yeah, that power of being vulnerable and being authentic in what you're doing and bringing that humanity to it, right? And how that can be scary and uncomfortable and also really powerful. Right?
I just want to say thank you to everyone for taking part in this, because I heard some amazing conversations going on, just lots of different ideas and riffing off of each other. And I think something else I got was, as people tried to explain their why, they started to realize there was maybe a bit of the science they didn't understand that could go back into the model development, which is, you know, this is an interesting two-way segue that it's not just because you're trying to simplify it doesn't necessarily mean that your science isn't there.
Yeah, I'll say that one thing that I actually love talking to non-expert audiences, which I think is very different in training sometimes we get as scientists or training we get talking to policymakers or media, is that it's okay not to know, right? And how human is that to not know things, and how inspiring can that be, right? It's such a great launch pad to talk about, you know, the diversity of STEM careers, right? Of like, oh, I don't do sea ice, I do land ice or something like that, right? That's a whole different topic, right? And other people are like, what? It's just ice. And so kind of you can frame it around diversity of STEM careers. You can frame it around science as an active process, right? Like it's not a set of facts that we know in a textbook, right? How do you counter that narrative? And then also just the wonder, right? That wonder and awe, that like how much of that inspired us as scientists, as kids, as adults, right? Of that curiosity. And so harnessing that when we don't know something or someone has, and like empowering someone of like, that's an amazing question. I want you to go find that or grow up to be that scientist, ask that question. Or, oh my gosh, I'm going to take that back to my team and build that into our model, right? Things like that. So those questions of not knowing can be really powerful, and like, don't be afraid of that or lean into that fear of that, because it's really great.
I kind of laughed at the interpretive dance idea, but at the end of our discussion, I realized that we could actually do an interpretive dance for our application. So I'm going to be in contact with some people about being some dancers.
It's going to
Awesome.
be a Earth System
And I
science
actually
talent show
understand some
coming.
teleconnections now as well.
It can be, yeah, I'm bringing in the arts. There's actually a SciComm workshop coming on performing arts that if you're on the community engagement listservs at NCAR or K-12, you might have gotten invites or might hear information about. But coming up, there's going to be a performing arts science communication thing. So I'm not teaching it. I'm not sure what it's going to be about. We'll find out.
Well, I'm really interested in the dance. I also really like that there was an example on this paper of a format of campfire stories. I was like, oh, that's a good one. So I'm just curious if anyone came up with, I don't know, an interesting or different or unique format for their storytelling.
Has anyone seen an interesting format that someone else has done, maybe that you haven't done in science storytelling?
Well, I can tell you kind of what I just came up with. So I'm a software engineer, and I've been at NCAR for a long time. So going back to the pre-internet days, and I was thinking of a presentation for kids of you go into town and you want to go to McDonald's. How do you do that? Well, you just ask ChatGPT or you bring up Google Maps and you say, tell me McDonald's, and it gives you directions. Okay, now put your phone away. How did we do it before that? And first step is you have to go find a phone book. So you have to explain what a phone book is. You have to find a phone book, look up McDonald's, find the address. Then you have to go find a map and
doing this with the kids to help them figure out how to get to McDonald's without their computer back with the old technology we had, I think would be something that would be kind of fun.
Yeah, adding props if you can get an old phone book or things like that too, to give that hands-on. Yeah, nice. Yeah. So yeah, if you have props you could bring ever when you're doing outreach or things like that, those are really great too, of getting that tactile piece or something that's relatable, right? Of like a phone book compared to the internet now, right? And having those analogies, right, of your props too, can be great.
Yeah, we did talk in our prep, didn't we, James, about how analogies were another form of storytelling. And credit to you, Cecile, for Minecraft and Lego. That just, yeah, as a way of communicating CESM. Yeah.
All right, we are just about right at 5 o'clock, so I want to let everyone go off to whatever they have next. But does anyone have any final takeaways, final share outs, or anything that you wanted to make sure that you shared before we all say goodbye today? Thank you. And thank you, Mari and James and Diamond online somewhere for organizing and asking us to be a part. And thank you all the presenters today. It was really wonderful. And thanks everyone for participating and sticking it out till 5 o'clock. So thanks so much, everyone.